Good morning, everyone. I request you all to kindly be seated. Good morning, everyone, and a very warm welcome to the inaugural session of the 3rd International Conference on Construction Materials and Structures, Synergy of Materials and Structures 2025, here at the esteemed IIT Tirupati. Nestled in the lap of the sacred 7 hills, Tirupati is often known as the gateway to the divine, a truly fitting location for such brilliant minds to convene. We are genuinely honored to have such an inspiring gathering of academicians, researchers, and professionals joining us today. To commence this auspicious occasion, let us seek divine blessings. May I now request everyone to please rise as we begin with a short prayer. गाइए गणपति जगवंदना गाइए गणपति जगवंदना शंकर सुवन भवानी नंदना गाइए गणपति जगवंदना सिद्धि सदन गजवदन विनायक कृपा सिंधु सुंदर सबलायक मोदक हर प्रिय मंगलदाता मोदक हर प्रिय मंगलदाता गाइए गणपति जगवंदना विद्यावारिधि बुद्धिविदाता मांगत तुलसी दास कर चोरे तुलसी राम सिय मानस मोरे तुलसी राम सिय मानस मोरे गाइए गणपति जगवंदना शंकर सुवन भवानी नंदन गाइए गणपति जगवंदना Thank you. With that serene beginning, let us now proceed further. I request the dignitaries, Professor Narayana, Professor Kodor, and Professor Novak, to kindly join the dais. I kindly request Professor Jain and Dr. Biji to accompany the dignitaries. I now kindly request the head of the Department of Civil and Environmental Engineering and the patron for the conference, Professor Suresh Jain, to kindly give the welcome address. Sir, please.
Good morning, everyone. I'm audible, right? So, distinguished guests, esteemed plenary speakers, keynote speakers, session chairs, respected colleagues, valued industry partners, dedicated researchers, and all delegates. It is with immense pleasure and a profound sense of honor that I extend a most cordial welcome to each and every one of you to the 3rd International Conference on Construction Materials and Structures, ICCMS 2025. Indian Institutes of Technology Tirupati, exceptionally proud to host this significant gathering, united under the pertinent central theme, Synergy of Materials and Structures. Over the forthcoming 3 days, from 3rd to 5th July, we are privileged to embark upon a journey of insightful discussions, innovative technical sessions, vibrant knowledge exchange. Our collective aim is to critically rethink the future trajectory of construction science and structural engineering, addressing the multifaceted challenges and the opportunities that lie ahead. In today's dynamic landscape, characterized by rapid urbanization, escalating climate challenges, and the transformative technology disruption, the imperative to harmonize material innovations with structural systems has never been more pressing. This year's theme, Synergies of Materials with Structures, rightly underlines the intrinsic interconnectedness between the advancements in material science and the ultimate performance of structural systems, which has to be safe and resilient. It is through such profound synergy that we are aspired to design and construct infrastructure that is not only efficient and economically viable, but fundamentally sustainable, resilient, and intelligent. ICCMS 2025 provides a timely platform to explore these critical themes, from the foundational material science to advanced construction technologies, fostering meaningful dialogue among academicians, practitioners, and policymakers. We are privileged to host distinguished scholars, industry leaders, and policymakers who bring valuable insights into the simulation-based design, concrete intelligence, decarbonization, and structural optimization. It's important to tell, like the Young Researchers Forum, participation from over 12 countries highlight our commitment to nurturing the talent and fostering global collaboration. Before concluding, it is my distinct privilege to warmly welcome our esteemed dignitaries on the dais, Professor Novak, Professor 𝗘𝗏𝗃𝗁𝗂𝗏. Your leadership and invaluable contributions inspire us all. We all incredibly fortunate to host an outstanding lineup of plenary experts. For example, if you say today, Professor Mike Schlaich, Professor K.V.L. Subramanyam, and Professor Narayanan. Your groundbreaking expertise will profoundly enrich our discussions. We are having 10 plenary sessions, and after first you will be having second day and third day. So I also welcome all my plenary experts in the day 2 and day 3 for gracing the occasion. On behalf of organizing committee, I extend our deepest gratitude to our chief patron, Professor K.N. Satyanarayana, Director of IIT Tirupati. Sir, your extraordinary leadership, unwavering support, and the constant encouragement were instrumental in making this significant event reality. This conference stands a testament to your vision. Thank you, sir, for your invaluable guidance. We sincerely acknowledge the dedicated efforts of the organizing team, technical committee, sponsors, and the students who are the backbone of this event. Without them, this event cannot be possible. For their unwavering support, made ICCMS 2025 a meaningful and impactful endeavor. As we commence this intellectually enriching journey, I encourage all participants to actively engage, share perspectives, and foster new collaborations. May this conference serve not only as a platform for knowledge exchange, but also as a catalyst for innovation, sustainability, and global global partnership in construction science. Together, let us strive to shape a built environment that is resilient, efficient, and environmentally responsible. Once again, I extend my warmly welcome on behalf of IIT Tirupati, Department of Civil and Environmental Engineering. I wish you all a productive and inspiring experience at ICCM 2025. Thank you very much.
Thank you, sir. Now I kindly request all the dignitaries to light the lamp and begin the session.
धनसम्पदः शत्रुबुद्धिविनाशाय 𝗘𝗴𝗃𝗁𝗁 ते 𝗘𝗴𝗃𝗁𝗁 ते 𝗘𝗴𝗃𝗃𝗶 𝗘𝗴𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃𝗃 स्तुतिर्जनार्दनः दीपो हरतु मे पापम् सन्ध्यादीपनमोऽस्तु ते ओ दीपब्रह्मरूपस्थं ज्योतिषां प्रभुरव्ययः ओ दीपब्रह्मरूपस्थं ज्योतिषां प्रभुरव्ययः आरोग्यं देहि पुत्रांश्च पतिं स्वच्छां हि मे सदा रवे
Thank you. Let us now extend our gratitude to our distinguished guests with commemorative tokens. To begin, I invite Dr. Bijli to kindly present a token of appreciation to our director, Professor K.N. Satyanarayana, as a gesture of gratitude for his presence and support. Now, Dr. Bijli, may I kindly request you to present a token of appreciation to the head, Department of Civil and Environmental Engineering, Professor Suresh Jain, in recognition of his continued guidance and encouragement. May I request Dr. Bijli to honor Professor Venkatesh Kodor with a token of appreciation. Dr. Bijli, may I kindly request you to present a token of appreciation to our esteemed guest, Professor Balthazar Novak. Finally, I request our head of the department, Professor Suresh Jain, to kindly present a token of appreciation to Dr. Bijli in recognition of her remarkable efforts and dedication, which have been instrumental in making this conference a success. I now invite Professor K.N. Satyanarayana to deliver his address.
Good morning, everyone. The dignitaries on the stage, Professor Balthazar Novak, Professor Venkatesh Kodor, my colleagues, Professor Suresh Jain and Bijli, and various other delegates from different parts of the world, my colleagues and students. Welcome to all the delegates for this conference. This is the biggest conference we have hosted on campus with about 500 plus delegates participating. So for the information of people who are visiting our institute for the first time or been here also earlier, the IIT system has been growing. Starting from the first 5 institutes, now we are 23 IITs. And we are, the IIT Tirupati was part of the 3rd generation IITs, as we call them, which started in 2015 and 16. So our institute started functioning from a temporary campus about 20 kilometers from here, closer to Tirupati town, in 2015. Now, typically, when these new IITs have started in most places, they start with a small soft launch with a few branches and a few students, about 120 students. And most of them have started with 3 branches with 40 students each. And typically, it's the computer science, it's the electrical engineering department, and maybe the mechanical engineering department, right? But when these IITs started in 2015, And one of the older IITs mentors has been mentoring the newer IITs. For example, in the second generation IITs, IIT Madras mentored IIT Hyderabad, and then in the third generation, IIT Palakkad and IIT Tirupati. The mentor director, IIT Madras was the mentor institute, and the mentor director, Professor 𝗗𝗃𝗏𝗏𝗃𝗏𝗏, said, no, we will have to start with civil engineering, given the country's need and so on, also, in addition to the other branches. So we started with 4 branches of 30 students each, both at Palakkad. Everyone thinks civil engineering is, we started civil engineering unlike all other institutes early on, because I had come here as a professor in charge to start it on behalf of the IIT Madras, and since I'm a civil engineer, that I pushed civil engineering early on, but I have to give the credit to Professor 𝗗𝗃𝗏𝗏𝗏𝗏, the mentor director from IIT Madras, for doing that. And of course, obviously, I supported strongly. So the point I'm trying to make is our institute, while most colleges, especially in the private colleges in India, are shutting down civil engineering departments because they are not getting students to join, shutting down mechanical engineering departments, core engineering departments as they call. And this is a great concern for the country. I'll come to that a little bit more. But more importantly, I would like to first touch on the theme of the conference, which is where they're talking about the synergy of materials and structures. Usually we have the materials guys having their conferences, the structures guys having their various conferences. And today, when I was walking along with Professor Novak, we were talking that, without a need for a structure, why do material research? But once you decide to build a structure, without the materials, you can't build the structure, right? So it's a continuum that needs to be tightly integrated. The both of them are not independent of each other. And bringing them on a common platform, people from both the areas. And we know how departments are also structured across various institutions. And they divide themselves into, especially in civil engineering, we have such a diverse area, starting from transportation to environmental to water resources, to structures, to geotechnical, and then construction, and then materials. And where is the materials positioned? Is it part of the structures group, or is it part of a separate group? Like me being from IIT Madras, early on, the materials group got out of the umbrella of the structures group and grew fast. I was also making the point that very often the materials group doesn't grow very strongly when it's completely under the umbrella of the structures group. But the point is that we need to work very closely, and they're not independent of each other. I'm very glad that this is being brought on a common platform. But since I've been given just 10 minutes, but this is my common theme that everywhere I go I've been talking about. And since I have the civil engineers here, if I'm worried about what's happening, is from a country's perspective and from the institution's perspective, that we are not getting good students to join civil engineering, right? That's a big challenge all of us have. And I know colleges where as I told, many of them are shutting down civil engineering. And if they're shutting down civil engineering, where's the feeder? Many of our own students at IITs don't continue in civil engineering. They get the civil engineering degree from IITs, but almost 70 to 80% of them move on to the finance sector or the IT sector or the business analytics sectors or the more paying sectors. And the input for us very often for our masters and PhD programs are from the NITs and the private engineering colleges and the government engineering colleges. And if the private engineering colleges are shutting down the civil engineering departments, and so the point I'm trying to make is, we say India still has to build 50% infrastructure more. What we have built, our Honorable Prime Minister has this call for Viksit Bharat 2047, that India being an advanced country by 2047. That is our 100 years after our independence. And if we have to achieve that, the foundation is your strong infrastructure. And we say that if you have to do that, we still have to, in the next 15, 20 years, we almost have to build as much infrastructure as we built since we got independence, right? Whether it's the roads, ports, water, wastewater, housing, commercial, power infrastructure, communication infrastructure. If you take all this, there's a huge investment that is required to do this. But on the other hand, civil engineering is the last branch to be chosen. For all other branches chosen, the students then choose civil engineering. And then many of the places I visited well-known private engineering colleges where in a section, they have only one section civil. They used to have 3, 4. They brought it down to 1, and only one student joined in 2023. Only one student joined. And they gave 50% concession on fee. So there's a big image makeover that is required from this sector for people to attract good people. And there is also a challenge that the industry is not able to pay. When I look at from our placement section, what is the salary that is being offered when a student graduates with a civil engineering degree compared to a student who graduates with a computer science degree? It's 3 times to 4 times they get more. So I don't blame the kids. I also say the industry also needs to step up to attract good students, nurture good internships, to bring them in, get them excited being in this field, excitement of building structures, excitement of building facilities. That excitement we need to create, right? And also the way we teach civil engineering is changing drastically. You cannot say that when I studied, I did 2 structural analysis courses, I did 2 concrete design courses, I did 2 steel design courses, I did 2 survey courses. The number of credits are being brought down, but at the same time, we have the infusion of data science, AI, which is starting to influence how we're going to be doing our designs, how we're going to be executing our projects, and so on. So the rapid change is happening from this perspective. How do we bring this together? Now, I think this is a challenge that all of us are grappling with, and if we don't act fast, and the rate of change is so fast, whether it is bringing in a lot more IoT-based solutions. For example, when we have structures, how do we monitor their performance? Any facility, how do we monitor its performance? How do you communicate the data that is by putting sensors and data capturing techniques, image processing and so on, and then how do you transmit it using communication technologies? How do you analyze this using analytics, right? And there you come into AI, ML, to routines on how to take actions, right? So there's a drastic change that is happening that we need to address this, and we need to look at things from a very much more interdisciplinary way. So I think there are a lot of deliberations. Fundamentals have to be addressed. We cannot compromise on that. Buildings at the end of the day have to stand. They have to function, but today that's just not enough, right? So I'm very thankful for all the delegates who have come to our institute, and as I told, we're giving, in fact, the Department of Civil Engineering, I think, related to any institution that started and the stage that we are, I think IIT Tirupati Civil Engineering Department is pretty strong. Our colleagues have been very active in involving in various initiatives at the national level. For example, one of the biggest irrigation projects in the country is the Polavaram project. Here in near about 500 kilometers from here. And our colleagues have been involved in the design of the dam. They've been involved in the design of the concrete that goes into the cutoff walls and so on. And they've come up with these designs which were taking about a year or so. My colleague Rahul and Janikramaya, they've got it done in 3 months, and with the international delegation group had accepted their solution compared to what some leading consulting companies were giving. So we are involved in many such projects. For example, Professor Suresh Jain is involved who specializes in air quality. He's doing air quality appropriate studies for various cities in the country. We are bringing in, and also the colleagues in civil engineering department have been very active in bringing sponsored research projects. We have two large facilities coming up, the National Facility and Rapid Prototyping of Pavement Surfaces. It's a 13 crores, 130 million rupees initiative, which the Ministry of Road Transport has funded here, which is where, you know, if you have to look at a new pavement surface material that you've created, you want to look at its performance, you put it in place, and then you have to keep it, vehicles running over it for months, over hundreds of kilometers or thousands of kilometers before you really assess it. Instead of that, can I take it in a circular way, you know, and that's the facility that is coming up in the campus. And again, with Biji and our other structures people, they have brought in projects on ultra-high performance concrete, two major projects, one with the Ministry of Road Transport and Highways, another one with the Ministry of Railways. So a lot of activity going on this front in the institute on 3D printed concrete materials. Then in all areas of civil engineering, we are growing. So we are really proud and privileged to host this conference on our campus, and look forward to the deliberations that are going to happen in the terms of the conference over the next 3 days. And also good that they had a pre-conference workshops and post-conference workshops. So I'd like to congratulate Biji. I've seen her work the last 1 year putting this together, and also all the sponsors. You see all the major construction companies in India, material suppliers, all of them have come forward to support them. So I'd like to thank all of them also for giving the support. And we look forward to this conference growing. It started off in Kerala, and then it's been expanding, and the support from all our international partners and delegates. Have a great time, and look forward to fruitful discussions. Thank you very much.
Thank you, Professor Satyanarayana, for your kind words. We now look forward to hearing from our esteemed guests. We have our first guest address by Professor 𝗘𝗴𝗃𝗃𝗃. Professor Kodor is a University Distinguished Professor at Michigan State University and a leading authority in structural fire engineering. His groundbreaking research into the behavior of materials and structures under fire conditions has made a significant impact on fire safety standards and infrastructure worldwide. In recognition of his exceptional contributions, Professor Kodor has been elected Fellow of 7 prestigious academies and societies, including the Royal Society of Canada, Canadian Academy of Engineering, American Society of Civil Engineers, and Indian National Academy of Engineering. May I kindly request Professor Kodor to deliver his address.
Very good morning to you all. Respected Director, distinguished dignitaries, invited guests, and delegates. It's a great pleasure and honor for me to be amongst you for this 3rd International Conference on Construction Materials and Structures. As you all know, the construction sector currently contributes significantly to the economic engine. For example, in most countries, it's about 12 to 15% of the GDP, and it employs millions of people in most countries. In India, it's tens of millions, as you know. And the ongoing construction boom in the country, although you call it boom, but when you look at our competitors, especially China, it is still nascent in its stage, right? So, and there is so much to be done in Tier 2 cities, Tier 3 cities, and more you are doing, because our prosperity of the people are increasing as well. Bangalore, 1 kilometer traffic, if you want to cover, maybe an hour sometimes. So still that requires a lot more infrastructure, a lot more this thing. So construction sector plays a key role, not only for the economy, but also for the well-being of the people, citizens, and safety and security of the country as well. Now, to address this, over the last 3 decades or so, construction industry is undergoing significant transformation. It's not only in India, but around the world, even from African countries, to US, China, India, everywhere. Basically, the serious problems we are facing today relates to sustainability, performance, right? Resource depletion. In Singapore, you don't get sand, for example. Vietnam banned sand, so Singapore cannot get sand. So how do you build, I think, So all these problems around the world, both political climate as well as socio-economic problems, have a significant impact on the way the construction sector is emerging. And added to this, we have carbon issue as well, which construction sector itself contributes nearly 1/3 of the carbon. You cannot change global warming without looking into how we are building, maintaining, as well as how we are using these buildings for energy, right, and other things. So all these things are added to this. Both man-made disasters and natural disasters are ever increasing, whether you call it wildfires, whether you are talking about tornadoes in the US, for example. All these weather patterns are changing. What it is making is it's making our structures much more vulnerable, right? All this to address these challenges, a lot of R&D activity is happening not only here but around the world, right? And this R&D activity, research and development activity, is bringing in new materials researchers are working in for addressing various issues such as sustainability, resilience, right, cost effectiveness and other things. In addition to this, we are coming out with efficient shapes and structural shapes and all this. Now, although this is happening, still when you look at it, the research is happening, it is not being practiced to a major extent because there's the limitations in the current core provisions, which are still reflecting of 70s, 80s, or 60s in many sectors or many aspects of the building design or structural design. The reason for this is basically it is not being transformed. At Google, your iPhone, every 3 months they want to take $1,000 for you from a new iPhone. But in construction sector, if you develop some new technology, it takes decades to put it into. I'm in a lot of codes and standards, both worldwide and US. It is impossible, right? So that means we are not achieving the intended final goal. So many of the codal provisions today, as I said, are reflecting from 60s and 70s, which doesn't apply to modern materials, modern structures, modern lifestyle, and modern practices. So in order to change this, right, what we need is events like this. So in this context, this conference is providing an ideal platform. And I'm very amazed to see so many people on the first day at 9:30, at 10 o'clock, that too in Tirupati, because many people who are coming in, in these traffic jams and stuff from other cities and stuff, airport delays. I'm amazed at the audience here, right? So this is providing an ideal platform to discuss latest research and development activities needed for improving our materials as well as structures, and what can be done to bring this into the field, right? Both from codes and standards point of view as well as the implementation. So over the next 3 days here, nearly 200 papers will be presented in various sessions. So I call upon all of you to utilize the opportunity to critically discuss the results and offer feedback to the authors or to the others to provide how they can improve whatever their presentations are, or findings are, and to implement how that can be implemented. Think about it, right? Also, please interact. There are audience from not only India but abroad as well, and top institutions in India, right? So mingle and talk to your colleagues who are attending here to learn about more research and technology, as well as to make collaborations for further interacting, because as the director pointed out, it's all interdisciplinary. We are not leaving either in both structural area or material area or concrete area. So you need different disciplines. It's really interdisciplinary. Finally, I congratulate IIT Tirupati, the organizing committee, especially Professor Biji and her team, has put up an excellent show, tremendous show, right? And in bringing various experts from not only India, from overseas as well. Last but not the least, I am amazed at the pace at which this beautiful IIT Tirupati campus has come out, and I am sure it's the blessings of Lord Venkateshwara was bestowed on this at the start of this thing itself. And within a short span of time, I've been to a number of IITs and NITs here. It has come out very nicely, both from the faculty, recruitment, and students' point of view, as well as from the infrastructure. So it requires really a strong leadership, as well as faculty collaborations, right, across the institute to bring this level. It's not easy to set up an institute and bring it in, in such a short notice. So I really congratulate the team here to making this institution as one of the renowned institutions, not only in India, but in the entire world. So if you want to look at it, walk around the campus and you experience it, you will feel it, right? How beautiful the campus is and how much infrastructure has come out. Fine. Last but not the least, enjoy the conference. Not only take some knowledge, take the blessings as well before you go, for your benefit and for the benefit of the construction sector. Thank you all.
Thank you, Professor Kodor. Now we have Professor Balthazar Novak with us. Professor Novak is the Deputy Director of the Institute for Lightweight Structures and Conceptual Design at the University of Stuttgart and a leading authority in structural and civil engineering. His pioneering research on pre-stressed concrete, seismic loading, and composite bridge structures has advanced European design standards and infrastructure resilience globally. May I kindly invite Professor Novak to deliver the address.
So, good morning, everybody. I hope you are fine and you are relaxed and you are full of energy to survive the next 3 days. I think it will become a very challenging, conference because we have a lot of topics. But I would like to start with the two speeches before. They have covered so much, so usually I could say hi and bye. But I will continue, and construction materials and structures. The title says it all. That means there is no possibility and and we should not separate materials and structures. Structures without materials are not possible. If no structures will be built, there is no need to develop new materials. That means we have a good energy, a synergy between materials and structures, and the material experts have to understand the structural engineers, and the structural engineers have to understand the material experts. And both have different languages. Material experts often think in reality, and the engineers, the structural engineers, they're thinking in moments, statical system, in tensors. But just with tensors, you're not able to erect a structure. And just with rheology, you're also not able to erect a structure. So both have to work together. And I would say not synergy of material and structure, I would say materials live in harmony with the structure. Because if you choose the wrong material for the structure, then there's no harmony between material and structure. And materials have weak properties, have strong properties, and the same happens with the structures. That means you have to avoid the weakness of the material properties at different locations where it is of disadvantage, and you also have to think of, okay, how can I make the structure in a way that the material can be used in an efficient way? For example, if you look to concrete, you have a very low and very uncertain tensile strength, so we try to avoid to activate and to use the tensile strengths directly. Indirectly, we use it because for shear we need it, for bond we need it. This is essential. Only without tensile strengths, no bond is possible. But usually we don't like to consider the tensile strengths directly. This is one example. And also in case of, for example, in case of structures, for example, when we look to steel, we have to be careful because of stability. If we make it too slender, then we have a stability challenge and we have to solve it. And sometimes it makes sense not to use steel, but other materials to avoid the stability problem. And those are just two examples to show how the different disciplines, they are not different disciplines, they are maybe different areas of one common discipline, are participating in structures and in materials. And now we have a new challenge with the development of the robotics and 3D printing. We have totally different requirements and boundaries which we have to consider. 3D printing, for me, is not replacing our traditional construction methods. It is one more flower in our basket. And we have to take care that this new flower will grow and will take their position in our construction engineering area. This is very important. And maybe finally, I would attract you all, the next 3 days, the stage is yours, and we have different lectures about materials, innovative structures, and so on. And I would like to convince you, the material experts, please attend to the lectures of the structural engineering part and the other way around, because you have to be able and you have to learn to understand the different language. Otherwise, you are not able to communicate, to work efficient, and to find the right solution, which at the end will lead maybe also a contribution to a more sustainable construction. Thank you very much.
Thank you, Professor Novak. I now invite Dr. Bijli Balakrishnan, Conference Chair, to kindly deliver the conference overview.
Good morning, all. Good morning to all distinguished guests, eminent speakers, delegates, and colleagues. It is both an honor and a privilege to present an overview of 3rd International Conference on Construction Materials and Structures. The inception of this esteemed conference series dates back to 2021, when the inaugural edition was hosted by IIT Calicut under the leadership of Dr. Blessing Scaria. This year's conference is being jointly organized by IIT Tirupati, Virginia Tech University, Queen's University, Monash University, IIT Bombay, and NIT Calicut. We are privileged to have with us today Dr. Alexander Brandt, Dr. Sri Nanukutan, Dr. Sudarshan Raman, Dr. Najib Sharif, and Dr. Jayachandran, whose presence and contribution have significantly enriched this initiative. The central theme of ICCMS 2025 is the synergy of materials and structures, a timely and powerful concept that reflects the evolving priorities of the global construction and infrastructure community. In today's context, the demand of infrastructure that is structurally safe, functionally efficient, sustainable, and environmentally responsive has significantly intensified. Addressing this demand requires a fundamental rethinking of how materials and structures interact, not in isolation, but as an integrated system. The conference theme underscores this need for convergence, bringing into focusing the critical alignment between material innovation and structural performance. The conference features thematic sections spanning a broad spectrum from high-performance concrete and fiber-reinforced concrete to performance-based design, durability-driven framework, adaptive structural system, and digital fabrication techniques. In response to the growing global focus on sustainability, ICCMS 2025 also address emerging priorities such as carbon neutral construction, recycling of industrial byproducts, and climate resilient design strategies. As government and industries across the world commit to a net zero goal, material research, design practices, and construction methodologies are undergoing a fundamental transformation. Through this theme and platform, ICCMS 2025 aims to support this transition by fostering dialogues and disseminating cutting-edge research and encouraging cross-sector collaboration. In essence, synergy of materials and structures is not merely a theme, but a strategy call to action, one that invites global engineering community to embed sustainability, innovation, and performance at the heart of every design and construction endeavor. Over the course of next 3 days, the delegates will experience a comprehensive program. The conference features 10 plenary talks, 21 keynote lectures delivered by eminent speakers in the field. We have received over 800 plus abstracts, of which 427 technical presentations has been selected and scheduled, which include 299 delivered in-person presentations, 128 virtual presentations, and 113 postal presentations. The presentations are distributed across 10 technical sections and 2 dedicated online sessions. We are also proud to announce 9 Best Paper Awards. The awardees will receive a cash prize and Ryland membership subscription. Each conference day begins with 9 a.m. with the plenary sections followed by lectures from our platinum sponsors. Afternoon sections are dedicated for keynote lectures and technical presentations conducted in parallel tracks. The valedictory section will mark the conclusion of conference in day 3. Yesterday, we successfully conducted 2 pre-conference workshops, and a post-conference workshop TLC2 is scheduled to follow. A highlight of day 2 will be our gala dinner, accompanied by cultural performance from the artists of Tirupati, offering delegates a glimpse into the rich heritage of this temple city while providing informal opportunity for networking, building professional relationship, and meaningful engagement beyond the formal sections. In closing, I extend my heartfelt appreciation to all collaborating institutions, our sponsors, and most importantly, our students, whose dedication and tireless effort are reflected in the seamless execution of this conference. I would also like to express my sincere gratitude to the Director of Institute, IIT Tirupati, and the Head of the Department of Civil and Environmental Engineering for their unwavering support and encouragement. I welcome all you to ICCMS 2025, and I look forward to the 3 days of inspiring discussions, valuable connections, and impactful outcome. Thank you very much for being here.
Thank you, ma'am. I now request all the dignitaries to join the audience as we proceed for the plenary sessions. We will now continue with the scheduled keynote talks. We have 3 plenary talks scheduled today. Please note that the plenary sessions are for 30 minutes, followed by 10 minutes of interaction. I invite our plenary chair, Professor Venkatesh Kodor, to lead us through the upcoming plenary talks.
Good morning again. So, our first plenary talk is going to be from Professor Mike Schlaich. Professor Schlaich is a managing director of Schlaich, German partner and chair of conceptual and structural design at TU Berlin. He is renowned for his innovative work in lightweight and expressive structures. He has led numerous award-winning projects worldwide and a distinguished member. He has been recognized as a distinguished member of several prestigious engineering societies and academies. I kindly invite Professor Schlaich to deliver his plenary address. Thank you.
So there is this.
Okay, I can start. Well, ladies and gentlemen, so many people, welcome to you all. Dr. Biji, thank you very much for the invitation. I'm very happy that I may be here, and to Dr. Professor Kodor for the introduction. I think the dignitaries with their introduction, little speeches, they gave a very good feeling. Oh, I get a microphone, so just give me a second. Where should I put this? I think the dignitaries told us very well the context of this conference and how important it is to not only think of materials, not only think of structures, but think it all together. Yes, we have to have specialists, but in the end we have to have this symbiosis and work together. My talk is perhaps a bit about the reality of this, how this ends up in the world of bridges. I want to tell you a bit about bridges, and I called it the responsible use of material, because in reality, let's face it, what we do as civil and structural engineers is big. We do big stuff that is expensive and that lasts for a long time. So there is a big responsibility, and that starts with the choice of material. And the choice of material is part of the whole conceptual design, because we do not want to build a concrete bridge or a steel bridge. We want to build a good bridge. And during the conceptual phase, we come up with the material and with the design. So we have this responsibility to choose the right material, the right structure, but I think our responsibility goes much further, you know. We have heard about the issue of sustainability. We should design structures that save materials. We have a social responsibility because our structures should do good. And finally, I think we have a cultural responsibility, because as long as it doesn't look good, don't do it. We want to go out of the house in the morning and see something nice, and not lots of piles and walls of concrete. We want to see nice stuff, and you can do nice stuff with concrete, but we have to do it consciously. I think that's very important. Anyways, I want to structure my short talk on bridges into 3 subjects. First, composite decks, where we join materials, and I think sometimes joining materials is very good. because then you get the best of all worlds. But we have to join them so that we can later separate them also, because otherwise we have toxic waste in the end. So we have to think in life cycles. Composite decks, our experience with bridges in India. Then I want to talk about integral concrete bridges, because I think they are very important if we think about saving resources and having robust, durable structures. And finally, I will talk about carbon fiber structures, carbon fiber materials in the field of constructions. And I do this in a way, as we say in Germany, I'm dancing on two weddings, because I'm working in an engineering office and at the same time as professor at the Berlin University. So I start with our office, Schlaich Bergermann it's called, and these are Mr. Schlaich, my father, and Rudolf Bergermann, his partner, and they have founded the office 40 years ago, and for the last 40 years we have worked in the field of designing bridges, roofs, lightweight structures, and I'll just quickly show you some of the bridges I will not be talking about, but I could just not resist to show you at least one picture, because this is a shell bridge made out of stainless steel. It's a 30-meter bridge with only 20 millimeter thickness. Due to double curvature, you get a lot of stiffness and you can walk straight on the shell. And we have, since the owner of this bridge sells laser cutting machines, we cut out holes so you can see the flow of membrane forces in the shell. So this is one material that was consciously chosen. Sometimes it's not the material of the structure itself, but the material you built in. Here, this is a bridge that we have just recently finished in Austria, crossing the Danube River, where the foundations were the problem, the rock was the problem. And here, actually, it was not a problem. We could finally do a bridge we have always wanted to do, a suspension bridge without masts, where the cables are directly anchored into the mountains. That you can only do if the material of the foundations is good, if you can anchor heavy loads in the soil. Or this is a design for a beautiful, transparent, lightweight arch bridge in Switzerland. And Switzerland is concrete country, but this is a steel bridge. So sometimes, you can switch even customs and traditions if you come up with a convincing design. And here, in this case, steel was the better solution. It's in the city of Chur, and in September there will be an international footbridge conference there in this city. And here, perhaps you know where this is. That's Tirumala, about 9 years ago, I was in IIT Madras, gave a course with Professor Devdas Menon. I think it was in 2016, and we did a workshop on bridge design with the students. So the idea was to design a footbridge for Tirumala, and later we made a concept study for a bridge to protect the pedestrians because they had to walk on the road. I'm not sure what happened to this bridge. Let's talk about this later. Anyways, just to give you some ideas, but our real root, one of the roots of our office is actually in India. Perhaps you know this bridge. I've been talking about this sometimes. This is the second Hooghly Bridge in Kolkata, the Vidyasagar Setu, that was designed in the 80s, and at that time it was the longest cable-stayed bridge in the world. It took a long time to build it. By the time it was built, it was not the longest anymore, but it was the first cable-stayed bridge with a composite deck. And it showed the power of composite sections, and it was built with local material, indigenously in a way, because at that time there was not really weldable steel in Kolkata. There was not a lot of experience with high-strength friction grip bolts, but yes, there was experience with riveting. So the entire bridge was built. It's a world record long-span composite deck cable-stayed bridge, and all riveted. So this is possible with local people, local workforce, local material, and local construction methods. Is there a pointer here? I don't know how the pointer works here. But anyways, you can see it. No, I wanted to pointer, that I can. No, don't worry. Let me go back. Here we were. Anyway, so this is local materials and riveting. So I think we as engineers, we have to be flexible and find out what is available and what can be done. And riveting is actually a very good way of connecting steel, even though today it's perhaps too expensive. So the bridge is still standing, and it shows how slender cable-stayed bridges can be, how resource saving they can be. It's a 450-meter deck with only a 1.50 meter height, you know. In our office, ever since then, we have designed most of our bridges, our cable-stayed bridges with composite deck. This is the 𝗘𝗃𝗃𝗶𝗹 Bridge in Hong Kong that has cost me 5 years of my life, so to say, but I do not regret a minute. I could spend a year in Hong Kong and I learned how to do, how a bridge is built. And I can only recommend to all the students, if you have the possibility, go to site and see how stuff is done. This is so important. That gives you a feeling. This bridge again is done with the composite deck. It's one of the few multi-span cable-stayed bridges. And again, 450 meter span and about 1.50 meter deck height. The difference to the bridge that we have seen before is that here we have worked with precast concrete slabs. You see a steel grid, and on the steel grid there's a concrete slab. And I think this is a very fast way of building such bridges, because the steel grids are comparatively light. They can be prefabricated and put on site very quickly. And then you have the sheltering concrete slab that protects the steelwork and takes the horizontal forces very nicely, the horizontal cable forces. But if you work with in situ concrete, these horizontal cable forces on the young concrete cause a lot of creep, and this creep then overloads the steel very easily. So this is why for the next bridge we have chosen prefabricated concrete panels, because they're older, so there's less creep and then less loading on the steel. So this is the example of the Hong Kong bridge, the 𝗘𝗃𝗃𝗶𝗹 Bridge, and because it's a multi-span bridge, you can see you have to stabilize the main pylon, and therefore there's these longitudinal stabilizing cables, because the central mast has no backstays, and usually cable-stayed bridges do have these backstays and they need them. Then this story continues. We came back to India. Perhaps you know this bridge, the signature bridge in New Delhi, which is a signature bridge because at the time the chief minister, Mrs. Sheila Dixit, she wanted an icon. She wanted a signature bridge, and when I hear this word, I get goosebumps, because usually I'm trained to do good bridges, not to do crazy stuff, you know, and signature sounds always a bit like crazy stuff, you know. But this bridge, to a certain extent, is not crazy, because it's leaning back, and the load of the mast that leans back is holding the weight of the deck, so that, yes, makes sense. But and there's a lot of symbolism in it. You know, you have this Namaste sign, and you have the two sides that hold the cable, so it's kind of an opening book, a new chapter for New Delhi. And since we had then, due to this shape, a lot of space here, we said, you know, why not paint it? All head wings of the airplanes are painted. Why not paint the bridge? But then how can I know what, as a German, what fits India? It was very difficult to find an all-Indian symbol, and after long discussions with Indian friends and colleagues, we thought that the peacock feather is perhaps the best. So what has changed regarding materials? The cheapest steel was from China. So in this case, the steel was ordered from China, while it was all Indian steel in the Calcutta Bridge. For the New Delhi Bridge, the times had become more global, and the steel came from China. I'll just give you one example what that means. If we look at just the connection here where the mast meets the deck, this is a rather big element that needed to be prefabricated, and that means that you have to move 400 tons of steel half around the globe. So this was prefabricated around Shanghai, plates that were welded together, and then you see the little holes bolted to longitudinal and transverse girders. It has to be coated, and they had to bring it from Shanghai all the way to New Delhi. And you see this plate here. This is a 250 millimeter plate. We thought that was not possible. We had designed it with lots of 50 millimeter plates, but the Chinese said, no problem, we can weld 250 millimeter steel plates. So the choice of material has also got to do with the dimension of the materials. What can you actually do? What can you weld? What can you connect? What can you transport? So this is just this little piece here. And the entire bridge was then built together like that. Because think, if you see such a mast, if you see such a pylon, how would you construct it? You know, what's the structural detail behind it? Is this hollow and the outer walls are load-bearing, or is there a structure inside? If you look at the Statue of Liberty, that was actually designed by Eiffel from the Eiffel Tower. The Statue of Liberty is a steel truss, and it's only covered by non-load-bearing steel plates. And here it's the other way around. Here, what you see is load-bearing. No? But this is material decisions and structural decisions. Does the material I have, is it able to carry the loads? And then you see these horizontal lines here, or these almost horizontal lines. This is also where individual elements were connected. It's basically a big Lego thing. Large elements were bolted together. You see the last one on top. So this is would be the size of one of these elements. So the bridge is standing nicely. It's fulfilling its task as far as traffic goes. But it's a bit strange, you know, why have a 250 meter, one single pylon cable stayed bridge in such an area where there's no water really, no? Because this is basically a 500 meter bridge with if it had two masts. So the initial idea was that all this would be somehow dammed, that there was a lake, a huge lake, and that would become a big park with a lake, you know. So they call it signature bridge, and whenever I'm in New Delhi, I say, yes, it's but the signature was the promise to make a park, you know, and you have not really fulfilled your promise yet, because this bridge only makes sense if there's a lake and a big park. So I really hope that one day this bridge will get its lake and make sense really. But it's a nice composite deck, and it really relieves traffic in New Delhi. Not all bridges need to be with composite decks, obviously. And here, this is an example of an all-concrete bridge, the multi-span extra dose bridge, the second Vivekananda bridge in Kolkata, designed by Parsons and IBT, together with CES, built by L&T, all these abbreviations. I found it very interesting to understand how extra dose bridges work, because I come from the field of cable stayed bridges, and if you see such a bridge as a cable stayed guy, you say that makes no sense at all. These very low pylons, these very inclined cables, the forces in the cables are way too high. Why do you make such a high deck if you could make it as slender as we have seen before? The backstays are missing, and this is all crazy. It makes no sense. But they are not cable stayed bridges, and this is why they do make sense for spans between, say, 100 and 200 meters. Basically, they are only box girder bridges where the pre-tensioning or the post-tensioning has somehow grown out at the supports. And these, since the cables are very shallow, the masts are very low, they work mainly to carry dead load, also because there's no backstays, the masts are comparatively flexible, and since the deck is very heavy, the deck is basically taking all the live load. So these cables that you see, they are mainly for dead load, they're basically nothing but post-tensioning, so the load-bearing behavior is completely different. And since they are mainly for dead load and they do not get stress changes because of, or no big stress changes because of live load, there's less fatigue problems. And if there's less fatigue problems, you can use cheaper steel and cheaper anchorages. And therefore, extra dose bridges are very, very attractive, very economic for smaller spans. So here concrete does make sense because you have these box girder sections, and you need the box girder section. Why? Because you have a central cable plane. So if there's loads on one side only, you get torsion, and for the torsion you need the box section, and the box section can nicely be done in concrete. So this is that I learned on site. We were the independent consultants, and I learned so much about extra dose bridges, actually, especially in India with all these well foundations. Well foundations are another very Indian thing. You know, you have these big rivers and the scour and the sand, and that all calls for these well and caisson foundations that you would not use so often in other parts of the world. So the well foundations cannot be seen. They are down here, up to 50 meters. Then you have this concrete pier, and you see the first segment still in steel, again, composite, steel and concrete. And then back there, you see it's all cast with concrete and all monolithic. So this is already an example of an integral bridge without bearings and joints, at least at the piers. And this is one of the segments, D6 segments, D6 because it's 6 lanes. There's all kinds of shear keys to connect the deck segments. Here you see this hole where the cables are installed. So very typical, and something that you would not build in Germany, for example. In Germany, such bridges are not allowed because in Germany people say in these joints there's trouble. We have a lot of de-icing salt in Germany, and the salt water runs into the joints, and then you get corrosion in the pre-stressing. So in Germany it would be very hard to build such a bridge, while in other parts of the world you see them all the time. Very strange. And also you see the stays. You see them in a steel sheathing, in a steel tube. And here the client said, I want to have a rather economic solution, not the expensive international long-lasting ones. I rather do a cheap solution that I can that I must replace every once in a while. So it was bare black strands that were guided through these tubes, through a steel tube in the mast, and then grouted. So imagine, we as independent consultant, we were not happy. We said, look, how does that work? You have these steel pipes, you have these bare naked strands, and then you just grout it. Who guarantees that this works? But we did tests on site. We did a trial, so to say. And you see this here, you know, this is the strands in the tube and all grouted. And then we were convinced there was hardly any void, so we could, through site testings, we could get convinced that all this would work. Extra dose bridges are also something quite Indian. There's a lot of extra dose bridges here in India, while in Germany there's not so many yet. This was one proposal that we did for a German Autobahn highway, but did not get built. Still, we got all the extra dose guys in the world, the ones that I know at least together. There's Mr. Sankaralingam, whom you perhaps know from L&T, and at YAPSE we wrote one of these YAPSE books on extra dose bridges. So we collected all the knowledge, that international knowledge that is available in this book. Thank you very much. So we have talked about cable stayed bridges and extra dose bridges and a little bit about the differences, but this doesn't necessarily have to be a steel cable. It can also be a steel plate. So this is a railway bridge in Stuttgart, Germany, that follows the same principle. You can call it an extra dose bridge, but rather than having expensive cables, it's just heavy steel plates that at the same time form a bit of acoustic protection. And this bridge was just recently finished. It's again a composite deck. You see the tent back there. This is where the deck was repaired, pre-welded, and then it was pushed segment-wise across the river. And you see the longitudinal girders and the cross girders. And then the concrete was cast on top. So even railroad bridges can be done this way. And underneath the deck, you see this hanging footbridge. So at the same time, it is kind of a protective, it's protecting the pedestrians that at the same time cross the river Neckar in Germany. This was the first part. How much time do I have left?
You have about 10 minutes.
10 minutes, okay, then I have to speed up a little bit. So integral bridges. In Germany, usually you do bridges with lots of joints and lots of bearings, and already my father, whom you have met in the beginning, said, look, why not make integral bridges with very slender decks and very small spans. The smaller the span, the lower the loads. You can do it with very slender piers. And this is what we have actually designed for German railways. German railways is rather conservative, but they have accepted integral bridges. So here you see very slender piers, very slender support structures with the starter reinforcement, and everything was concreted together as an integral bridge. So no bearings, no joints, for very few joints, and that is, I think, a very elegant way of building robust and low maintenance bridges all over the world. This is yet another example, a bridge that is 600 meters long. It has several segments of 600 meters, so every 600 meters there's a joint, and you see how slender the masts are, because they have to take care of temperature movements. If you have no joints, that means you have quite some movements due to temperature. But if you define well the concrete, and in this case you have to define not only the strength but really the modulus of elasticity, then you can do very lightweight, very elegant, very resource efficient structures that last for a long time. But in this case, yes, the movement goes all the way into the ground, so you have to also do pile-soil interaction. Calculation becomes very important. And this is also my claim here. You have to spend a lot of brain as engineer, and the contractor and the client are the ones who save money, so they should pay us well, you know. If you don't pay your engineer good fees, he has no time to do stuff like that, you know. So I think it's very important that contractors and clients understand that. So this is the bridge, and you see even at the joint, there is no bearings, because there's two walls on the mast, on the pier, and these walls are monolithically connected to the deck. We applied the same system to highway bridges, and you can see that it's a very humble highway bridge, but still small spans, only 1.20 meters height, and very slender piers of high strength concrete that can take care of all the movement. So this is 600 to 700 meter integral bridge without any bearings, any joints, and they are very cost efficient. So because there's no expensive bearings and no expensive joints. But yes, you have to sometimes construct the piers and stress them to the side, then cast the concrete, and then with time they go straight due to creep and shrinkage. You have to do some fancy construction acrobacy sometimes if you really want to do it successfully. So you see how slender these piers are for a rather normal bridge, but the contractor saved a lot of money and the world saved a lot of resources. So I have about 5 minutes left. 2. Okay, now we go into the field of carbon fiber. Perhaps we can discuss this later, because these bridges are pre-stressed with steel, and we have started to work with carbon fiber. This is perhaps the first carbon fiber stress-ribbon bridge in the world, about 15-meter cable, stress-ribbon bridge with only 1 millimeter structural height. You know, very slender, because carbon fiber does not corrode, no fatigue, and very lightweight. So I had several PhD students working in the field of carbon fiber cables. We have developed anchorages for carbon fibers. I could talk for hours, but this is not the time right now. I just tell you, don't break them. Make sure that this brittle material doesn't break, because you end up with a lot of fibers and a lot of powder, black powder, after a big bang. But this research has led to bridges like that. This is a network arch bridge where you get a lot of stress changes to life load, and if you would make the hangers in steel, they would have big diameters because of fatigue design, while with carbon fiber you can end up with very slender hangers, as you can see here. The entire bridge was prefabricated. This is the carbon fiber anchorages, and here you can see how slender these hangers are in carbon fiber. There's another bridge I quickly want to show you. This is the Oder. Oder is a river between Germany and Poland, and German railways again allowed the change from the heavy steel hangers to the lightweight carbon fiber hangers because it meant lots of savings for them. So this is another railway bridge where the bridge is pushed in and eventually goes 120 meters across this river. So you see how slender the hangers are. And in the last minute I have, after the opening, I'll show you some university stuff. So this is no explosion, it's the opening fireworks. So they have some, I didn't know that there was daylight firework, but there is. We have developed now pre-stressing systems for concrete girders. So we want to do bridges that consist of individual carbon fiber pre-stressed girders that are cast into the abutment. And we have done tests now. This is a 1:2 scaled example of such a precast girder cast into the abutment. So you have no joints, no bearings. You end up with an integral bridge. And we have loaded it very heavily, as you can see here. Then with a shaker on top, we did 2 million cycles, and we found out there is no fatigue issues in carbon fiber. And we are now trying to do this with small elements. We do computer tomography to see what the joints say to that. You know, if you do computer tomography, you see all the little cracks in the concrete. We can check the surface and how the surfaces are connected. And we've actually built a small test bridge. You see these small precast elements, and they're stressed together with carbon fiber. And we could prove that these carbon fiber pre-stressed bridges work very well. So you see the carbon fiber strands here, pre-stressed together of lots of little elements. And I see a lot of future in the field of carbon fiber pre-stressing also. So this was a quick run through the world of composite decks, integral bridges, carbon fiber, India, Germany, and I hope this entertained you a little bit and inspired you to think about materials and structures. Thank you very much.
Thank you very much, Professor Schlaich. So now is the time for questions. We can take 2-3 questions. So who wants to go first? Yeah, please go ahead. Yeah, take the mic so that everyone can hear you, please.
Hello. So good evening, good morning, sir.
Good morning.
So my question is that you have just now told about the bridge deck and the piers connection, monolithic connection, and without any bearings. So basically we know that bearing also helps in the seismic effect and also for the expansions. So how you are providing that in this without any bearings? Can I get to know? Thank you.
Well, you're talking about seismic effects, right? I think if you have an integral bridge, necessarily it can much better redistribute forces. You know, it's not a single girder that falls down when there's an earthquake. It's not a continuous deck on supports that works only by itself. It's one monolithic structure. So in the case of earthquake, bending moments can be redistributed much better. Not only that, since it's an integral bridge, you know, the section will be much smaller, you know, because the moments, again, it's not a single girder. Since you use less mass, and in earthquake it's force is mass times acceleration. In lightweight structures, the forces due to earthquake are lower. Yes, you need, in the end, you have to cater for earthquake, but I think in general, integral structures work better in case of earthquake than single girders, say. That's my experience.
Okay, next, let's move on. Yeah, please, go ahead. Mic there, please.
Good morning, sir. Sir, in the Belgium bridge, you had a kind of a structure. You have designed a very slender structure, and how does it take load in the out of plane direction? Like in plane, probably it will take that integral. And yeah, this bridge. Lateral loads, how it.
Well, it takes the lateral loads without the bearings. You know, if you had lateral loads, if you had piers and the deck and bearings, you know, the lateral loads had to go through the bearing. Now there's no bearing, so the lateral loads can be transferred very nicely. You mean the transverse load, right?
Yeah.
Yeah, they can be transferred very nicely through these slabs into the ground. There's no problem whatsoever.
If there is some shaking, like earthquake or something, earthquake and ground motion.
Well, I must admit that Belgium is not a very high earthquake zone, I agree. But again, I think this is easily possible because as long as you consider soil-pile interaction, you know, you have to model the entire structure all the way into the ground, and then seismic analysis is not a big issue. Thank you.
Any more? Yeah, please, go ahead.
Good morning, Professor.
Good morning.
I'm R.N. Dubey from IIT Tirupati. I wanted to know what is the longevity of the carbon fiber bridge, because we know about the steel bridges. It has been going on for years and years. What is the longevity of the carbon fiber bridges?
Yeah, this is the $1 million question, because no one has 100 years of experience with carbon fiber, right? So we don't really know. What we have done is these fatigue tests with millions and millions of cycles, and we know there is no fatigue issues, right? But carbon fiber reinforced plastic, that's the name. There's a lot of plastic in it. 50% is plastic if you look at the section. And we do not really know how long these sections, how long the plastic lasts. You know, that is perhaps the problem. But all the tests that we have done so far indicate that they're behaving quite well, you know. The main issue is fire, you know, so these carbon fiber reinforced sections should not be exposed to fire. That is the problem. But in the case of the railway bridges, German railways was relaxed, you know. They have some sheathing, some cover, and that's enough.
Yeah, we'll take one more question. Yeah.
Good morning, sir. Sir, I'm Aparup from Larsen and Toubro. I will be continuing with the same question. You did external pre-stressing with the carbon fibers or internal? And did you find any anchorage breakage or any such things happening in that?
Well, the fibers, since they are fibers, you cannot anchor them yet like you would anchor a steel strand. You know, if you anchor a steel strand, you have these steel wedges that bite into the steel. It's impossible for carbon fiber. So the anchorages that are used and that we have developed are anchorages where the fibers loop around a bolt, a pin, you know. And these loop connections, they work very well. So far, we have done lots of tests. Yes, I've seen lots of failures, but only during testing, you know, because we test until failure. But with the structures we have done so far, nothing has happened. They're behaving beautifully. I'm very surprised, and that's why I see great potential in the field of carbon fiber.
Professor Bijli.
Yeah. I have a question for the integrated bridge here. How about long-term effects? Like we have effects from creep shrinkage of the material.
Yes.
When we do this analysis of these bridges, the input for the analysis, which is supposed to be the time-dependent parameter of this material,
yes.
Are we taking it from a standard, or are we evaluating the material we are going to use in that particular structure and getting the material input, that particular property what we are looking at as a time-dependent parameter, as the input to our analysis?
Yes, it is. I think it's very important that we know all that. As I said, you know, if you build such a bridge and then you get, due to creep, because there's a lot of creep because they're pre-stressed, you know, you get a lot of bending in in the piers. So we have to build the piers pre-bent like that, and then they creep back into the vertical position. So you have to know very well the modulus of elasticity. You have to know not only the strength, and you have to be able to predict as precisely as possible the creep behavior of the concrete you're using. So a lot of testing was needed for these bridges. That's what I'm saying. You have to invest a lot of brain and a lot of testing in the beginning, but then you're sustainable because you save a hell of a lot of cubic meters of concrete, you know. And I think this is the way we have to think today and design today together with the material experts.
Thank you. Thank you very much.
Okay, last question for me.
Please.
Make an exception. So, lightweight structures are excellent. You reduce the mass, achieve cost effectiveness, sustainability. Also carbon materials, extra strength, everything adds up. But recently there have been number of fires on bridges in the United States compared to before. Major fires, yeah. Major bridges, like if you know I-95, I-10, you name it. And especially when a diesel tanker, oil tanker hits, or a train carrying a lot of oil goods. So how vulnerable are these bridges? Is it accounted for? Either due to this or even terrorism, for example.
I fully understand what you say, and I think we should not overdo it. And lightweight is not always the solution. But since you had a but, I also have a but. But I think that lightweight is not necessarily the only problem. With, say, in case of fire, heavy weight is not necessarily the solution to fire issues. Or if you take a terrorist or bomb attack, a lightweight structure is very flexible, you know, while a brittle, heavy structure could even fail earlier. As far as, like, to take Baltimore and ship impact, yes, you have to have good ship impact. Every bridge needs good ship impact, no doubt, you know. But that's not related to the proper structure, because if a tanker hits a deck, no matter what the deck is, the deck will fail. But you're right, you know, lightweight structures are not always the solution.
No problem. Thank you very much for the excellent session, first session.
Thank you.
Thank you.
Thank you, Professor. We will now take a 30-minute short break for tea and refreshments. Kindly return to the same classroom for the continuation of plenary talks. Welcome back, everyone. I hope you had a refreshing break. We will now resume with our plenary sessions. I now invite our plenary chair, Professor Venkatesh Kodor, to kindly come forward and carry the session ahead.
Hello again. Hello, you can hear me? Sure. Okay. We will move on. This is the second plenary session. So in this session, we will have two talks by eminent experts. The first one will be given by Professor Ksvl Subramanyam, who doesn't need any introduction anyways. But I have to do this in order to keep equity, you know. So Professor Subramanyam is a distinguished professor of civil engineering at IIT Hyderabad, specializing in structural engineering, blast mitigation, concrete durability, and 3D printing as well. He has made significant contributions to research, teaching, and innovation in infrastructure, monitoring, and rehabilitation. May I kindly invite Professor Ksvl as his
fondly called to deliver plenary address. Come on, Fia. Perfect. Okay. So thank you, Venkatesh, and thank you to the organizers for calling me here. I know we are the second plenary slot, which I'm sharing with Narayanan. So I want to make sure that he gets enough time, so I'll keep my presentation a little quick. Well, I mean, what I'll be presenting about is form optimization. I'll introduce this concept. Basically, in some sense, I'll take you back in history, why structures in the past have stood, without using any steel in them, because our ancients somehow figured out structural forms that are very efficient, that use material like brick, mortar, masonry, to their functional advantage, where they were put primarily in compression. So can we exploit that with 3D printing? That is the idea. The other thing I wanted to highlight here is exactly the theme of the conference, and that is, this is good enough, right? Yeah, I'm happy with this. And the theme of the conference is linking material with the technology with the structure. And oftentimes we see things slip through the gaps when you're trying to bridge these three domains. People who work in material advancement work in their own silo. Often they're not interacting with the structural engineers, and they're not interacting in turn with the technologists who are developing the technology. So rarely do you get something where all three can be used, and with this particular technology, if all three of these domains don't advance together, there is going to be no advancement. This will fail as a technology, I think that is mentioned in the inaugural session. So I did want to introduce my team. We of course have a big team of researchers. I'm working with a startup company that basically has all the fun. They're the ones developing the technology, and then of course I'm working with structural consultants who help me with the structural, integrating whatever we do with the structural concepts. Now, with this, I just want to quickly touch upon what 3D concrete printing is and the niche that we hope to fill with this. First thing is, the current form of construction that we have is slow. And it by itself requires forming. You need to construct shuttering, assemble your shuttering, pour your concrete, and then slowly it takes shape. Now, of course, you can say forming on site is an advantage, but it's also a disadvantage because I'm limited to rectilinear shapes. Now, when you're talking rectilinear shapes, they are not the best shapes possible. They're not the most efficient shapes. What are you doing? You're packing a lot of weight, and to support that weight, then you need more weight. So basically, you work down a negative spiral, a downward spiral, where if you look at fundamental concepts of design, the way we work on design is that I try to design a beam. Usually it's rectangular. That's the way we are taught beam designs in reinforced concrete. And the way we do it is we assess the demand. Usually most of the demand, particularly with larger spans, comes from the self-weight itself. What do? We try to balance it with internal moment of resistance that is generated by the material or a combination of materials, steel and concrete. And if the material resistance is not adequate, what do? We make the beam deeper. In doing so, what do? We add more weight, so that adds more demand, and what happens? We go down a negative spiral. And most of you who have done reinforced concrete design know very well that beyond a certain span length, you cannot do a singly reinforced concrete beam. You just cannot, because you go down in a negative spiral. It's like a dog chasing its own tail. So now, can we do something about this? Can we actually not use material where it is not required, where it simply adds weight, produce functional forms that are efficient, and in the process produce lightweight structures which are functionally efficient. So we are not compromising on any of the functionality part, be it strength or stiffness or any other performance measure that you may take. And of course, one of the advantages of 3D concrete printing is that you can print a structure. You don't need form. It's form-free construction. And that is an artist's rendition of what we hope to achieve, is basically a robot printing its way, thinking its way out of, give it a problem, and it's an AI-assisted robot that basically starts at one end and builds a bridge that goes to the other end. Well, that's a far ways away, but the whole point is that we want to use this concept of rapid lean construction using form optimized structures which are possible. Now if you look at that particular shape that is printed out there, that would be the shape of a bridge that would come out of a process called topology optimization. Where topology optimization, you basically optimize the structure, take away material where it's not required, and you end up with something like that. Except printing something like that in reality is still farther away. We have certain constraints. And what are the constraints that we are currently dealing with this form of printing? What we are currently working on is this layered printing. We assemble a structure in layers. Now, one of the fundamental challenges there is the development of the structural form itself. I can develop all the technology that I want, but if these filaments that I'm extruding, if I don't assemble those filaments in a structural form, then I've not basically achieved anything. I can build walls all I want, but those are simply walls. But can I do something by using this structural form that I can develop, which allows me to use the material efficiently? And that is the first challenge that we are facing. Integration of reinforcement still remains a very big challenge. The determination of structural performance, in fact, I was presenting on this yesterday, where how do you determine the material property? And I'll show you a little later. There is no unique material property in this layered assembly. When you talk about compressive strength, it varies with the direction. And the second thing is, how do I translate what I measure from a small cube or a cylinder onto to project and predict the behavior of a structure? We are still far away from there. We are still not at a point where if you give me the material properties, I can tell you how the structure would behave, particularly for these layered assemblies. And continuity in the structures. When you're talking about concrete structures or steel structures for that matter, continuity, the flow of forces, transfer of stresses is very, very important. So we have to visualize the flow of forces, the stress paths, and make sure the material is adequate to withstand the stresses. So we started with this, and we wanted to demonstrate this process of form optimization, and we chose a bridge for our purpose. The whole point was to demonstrate this form-specific structural system optimization for this specific case of bridge. The idea was very simple, that we were going to design and print a bridge of 7.5 meters. That was the design purpose. Go through the whole process of this form optimization, come out with a structural form, and actually design the bridge, test it also. We've tested some prototype bridge, and then finally install this bridge. That is the bridge that is installed on our campus. It is designed as a pedestrian bridge. Although when we tested for load capacity, it has significantly higher load capacity. It could very well pass. It could certainly take the traffic, regular traffic, for a 7.5 meter bridge. So now, when it comes to developing the printing bridge, we have to assemble. We are looking at filaments. So basically, what comes out of the printer is a filament. It's an extruded filament of concrete that you deposit and create a contour. And that contour, you assemble several contours in multiple layers, and you create a structure. So that's how the structure is built. Now, the first thing we had to do was develop the material that would basically withstand the rigors of printing. Now, I will not get into details of that, particularly dealing with printability, buildability. There's a lot of material processing that happens, development of the material itself that makes a material suitable for printing. I'll not talk about that here. Then, of course, the form optimized structural system. That's something that I'll present here in detail. The construction methodology and field direction. Early on, we decided that we were going to do off-site printing. So it's essentially like precast, except we print the bridge, segments of the bridge, integrate them on-site. So that was the idea of the bridge. Then, of course, we're going to field test it and calibrate our numerical model, which should give us some sense of confidence if we're going to predict, and then do a field deployment. So the printing system itself, it's a custom engineered printing system that we developed. It's different from most other commercially available systems in the sense that it's a direct deposition system. We have a custom engineered pressure control pump, which with a PLC controller, which allows us to control the output at the pump. We do not have an additional compactor that's available in most printing systems. The material directly flows from the pump to the nozzle. The nozzle itself is a commercial make. It's an ABB robotic arm. And it helps position the material and deposit the material along the contour. So this is the system that we have developed, and with this we are able to print concrete with about 6 millimeter sized aggregate, which I know for those of you who are working in concrete perhaps seems not significant, but in printing community I think that's considered still pretty much the cutting edge. Now, this is what you get from the material. So this is the extruded material, there is the print direction. When you're talking about printed material, you have to be very wary of the fact that you have to align, you have the physical dimensions and then you have the material directions. You have to always align yourself with the material direction. Because the material is extruded in a certain direction and then it is assembled in the form of layers, so typically we assign the print direction and the two orthogonal directions. And when you actually test this material, this is the material that we had extruded. This is what we got as strength. So you see that the strength in the three material directions is different. Now, not just that, of course, you get a lot of variability. There are reasons for that. But the anisotropy is evident. You have basically a transversely isotropic behavior or perhaps even an orthotropic behavior. Now this gets us out of our comfort zone because we, everything that we do with concrete design, we treat it as an isotropic homogeneous material, which basically means the material is behaving the same in all directions and at all locations. That's not true here. You have these layers between, you have layers and they're separated by interfaces, which creates anisotropy, and that is reflected in the material properties. Now, if I was to design with this, which material property do I use? So, being good engineers, here's what we did. We chose the weakest direction, which is direction 2, and then we said, well, we are going to apply, take 1.65 times standard deviation, we move away from there, define a characteristic strength that comes out to 30 MPa, and we thought we can't go wrong. So that's the compressive strength of our printed filaments, and that's what we are going to use and proceed with our design. Now, the next thing is reinforcement. So initially we thought, how do you put reinforcement? And if the whole process of depositing concrete is automatic, then maybe we should also put steel in an automatic manner. So simplest thing we could think was to cheat, and that was to put steel, essentially a steel wire between the filaments. Each filament is about 50 millimeters thick. We simply put a wire of steel there and print on top of that. So this is, there's no special, nothing special done to bond the steel to the filaments, and the bond develops as the concrete hardens. So we wanted to see how effective is this. And so we did some fracture tests where of these beams that are printed with the steel placed between two layers. And in fact here you can probably see, if I can get my pointer working. So here you see this is the, there's a notch, the steel was placed at this level here. We did the fracture test, and from the fracture test we basically extracted, this is the load response that you get, not very encouraging, but there is still something we can salvage from here. So if you look at the load response of this beam that is tested in fracture, load builds up to a high value, a crack forms, you can see the progression of the crack, and then steel eventually does catch up. So the steel starts giving a response. Mind you, this is just a 3 millimeter steel wire that's simply placed between the two layers. And I'm able to get some residual force transfer from this concrete by just simply placing the steel between the layers. And we can actually do some fracture analysis, and from here we can extract what is called the cohesive stress. What is the residual stress that the steel bar is providing? And if you see the orange line over there, that is the residual stress of concrete by itself as it's fracturing. The top of where the curve intersects the graph, the cohesive stress at zero crack opening is the tensile strength. And as you start opening the crack, you see for concrete, the cohesive stress steadily decreases, comes down to zero. But when you put a steel bar in there, you are able to get some little bit of residual stress in there from this tiny little steel bar sitting there. Now, and I'll park this here. I'll show you that while it doesn't seem very significant, it actually plays a big role if you get your system, the configuration correct. So next thing is development of the structural form. So here's where we started working on the structural form, and I'm literally showing you a scan of my notes as I was taking when we were having these discussions about the structural form. The idea was to use the concept of a tied arch. So you have concrete in compression, which is tied with a tension tie. So you separate out compression and tension, use concrete to its advantage, we know it's strong in compression, and simply tie it with a tension tie, which could be a steel tie, which would be just basically holding it together. Now within the compression arch, I have to still develop a compression form because I'm printing in filaments. So that is the very first step we took at developing the structural form, where you have the filaments. Basically each one of those green lines is a filament that is being printed. So that was the grand concept that we were looking at. for developing the structural system of this. Now, the other thing is, if you think about this, the filaments are basically being placed in those the green lines that are shown there. And as the printer runs along, the filament would be deposited in the strongest direction. The strongest direction of the material is the direction in which it is extruded, and the material would be placed in the strongest direction along those the members of that particular structural form. So by default, I'm using material, the strongest direction of the material is oriented along where the stress is going to be the highest. Now, but we wanted to develop this further, and for this tied arch, we were relying on this geometry-based development of stress. Now, if you take a beam, you'd apply a uniform distributed load on it, you'd see from the stress contours that you get a compression arch that forms on the top. Basically, the entire compression goes onto the top, which can be carried by the compression, and the bottom part of the beam would essentially be in tension, which you can remove. And that's where you can put a tension tie. So our whole concept was to look at the compression form, which is what we get from a stress analysis. This would be the concrete part, and then we would rely on steel to take the tension. It could be steel, or I could even put abutments and simply transfer the thrust onto the abutments, because all I need is something that takes care of the lateral thrust. So we went about developing the structural form, and for this we were using the truss design from this stress trajectory. So you can do a stress analysis, identify all the stress trajectories. The compression form comes out in the form of the outer boundary, which is the top surface and the side surfaces. And the bottom parabola is basically what you get from the compression stress trajectories. Once you get the compression form, you can develop the structural system, a lattice grid of members inside that compression form using the Mitchell truss theory. What you do there is you look at the continuous stress field and replace that continuous stress field by these lattice members. So you create a structural system within the compression form. Now, that is the process we followed. This is the first tab of a structural system we developed within that compression form. You have the top chord, the compression arch, and the two sides, and we've basically created a lattice inside there. Now, when you do the analysis of this lattice, what you find, and the analysis is shown on the bottom here, you see that the diagonal members alternate in compression and tension. That's what is expected when you have a lattice of diagonal members placed within the compression arch. Now, the top chord actually does see some flexure. There is some bending that happens there. So these are things that we need to worry about when we're doing this. And of course, the strongest direction of the material is oriented, is placed along the members, the filaments that form the structure. One of the problems with this particular geometry is that we have these 4-member intersections, 5-member intersections, and when we are printing using in concrete printing, in one layer, you basically want a continuous print path, and when you have these 5-member intersections or members crossing each other, you do not get a continuous print path. So the next step in the evolution was to go to a 2-piece bridge. Now here, if you look at it, the diagonal members essentially are continuous. You do not have these 5-member intersections. And if you look at the two pieces, the left and the right piece, which would be printed separately, I could print each one layer in one continuous motion without having to lift the print head. So here I get print path continuity here. We did the analysis, and basically from here then, the next thing, if I can just go back. So if you look at the structural member here, I have the arrangement of the structural members, the diagonal members within the compression form, and the height of the arch. So I can play with the height of the arch. When I actually increase the height of the arch, I actually see that the stresses go down in the members. And if you look at this as a structural problem, what I have is a geometry that I'm trying to optimize. The compression form is given by the stress trajectories. If you remember, the top chord is fixed, the side face is fixed, the bottom arch comes from the stress trajectory, that part is fixed. Then I have these structural members, which is the lattice, which I can play with. I can actually increase, decrease the spacing of the nodes and create different structural forms within this compression form. The other freedom I have is to play with the height of the arch. I can increase or decrease it. So we did this process iteratively and went through several iterations, and from there we ended up with a final configuration that you see at the bottom here. And the constraints we had was stress in the members, primarily tensile stress, minimize the tensile stress in the member, and minimize the deflection in the structure. So we are able to actually cut down the deflection, and significantly the self-weight of the structure contributes to the overall deflection. So basically, when I take away material, I'm actually helping the structure by reducing the demands. And that in turn reduces the stresses in the members. So this is the final configuration that we have, that we settled on, which gave us the best performance in terms of deflection and stress. Now from here, the next step is to was to actually print a prototype bridge and test it. Now the prototype bridge, we couldn't do a full 7.5 meters. It is a scaled down version, so everything was essentially shrunk down to a smaller 5.5 meter span. But of course, when you shrink it, your print filament thickness still remains the same. So it's not exactly scaling, because the filament thickness is always fixed when I print it. So this is the scaled down version. We printed this prototype bridge, that was installed. We tested it, excuse me, load tested it. And the idea of this load testing was to calibrate our numerical model. And when we actually looked at what we were predicting, we were pretty close to the deflections that we were able to get within the linear part of the load response. And by then we were already hitting serious loads of about 40-50 kilonewtons. And when we started loading beyond that, the response was still linear. But my students didn't allow me to load the bridge further. They did not want us to damage the bridge. They got really attached to the bridge, so we had to leave it at a certain point. And I said linear calibration is good enough, and so my model effectively works from there. Now, the next thing is to actually print the 7.5 meter bridge. We reinforced it by using the same wire. Now, this is the reinforcement template. Again, just doing what is expedient. Just simply take a wire, bend it in this shape, it's a continuous filament, and every 8 layers would simply lower one of these steel wire templates onto the, or I should say after 8 layers, we would basically lower one of these steel templates, which is again a continuous run of steel, which is placed between 2 filaments. And we already have the tensile response, the cohesive response that we got from the fracture test. So I do get some residual tension resistance from this steel template. Now, next was to simulate the response. Here we are getting into now predicting it using nonlinear finite elements, using concrete damage plasticity. A proper model was built, and the idea was to be able to predict the load capacity. How much can this bridge possibly take? And here again, we're cheating a little bit, because we've only done the linear calibration, but we're pushing our simulations to see how far, what load the bridge could actually take. So here is the load response that we got. That's the curve in the blue. And we see that it actually goes to a pretty high stress, the pressure that can be applied onto that. It goes to about 64 kilopascals or so. That is the pressure that can be fixed before serious damage starts to happen. Now, if you look at the damage in the bridge, you see that most of it is tensile. So basically, the tensile members, the diagonal members, crack first, and that little bit of residual stress that the wire is able to provide, what that does is that it basically redistributes the forces within the lattice. So you don't need a whole lot of tensile capacity to be able to redistribute forces within the structure. And that's what's happened. So if you look at point 1 is where the first crack happened. And after the cracking, the steel takes the tension. The residual stress is small, but it still takes it. And because of that, there's a redistribution of stress within the entire lattice structure. And that allows the load to build up to a significantly high value. So while the first cracking happened at 30, it essentially failed at almost double that load. And while it went from point 1 to point 3, there was a lot more cracking, a lot more diagonal members cracked, and there was a little bit of residual stress that the tension wire was providing. The final failure happens because of the compressive strut. When the compressive strut fails, one of the members that's loaded in compression, when that fails, the structure goes. So that's it gives us a reassurance that even with a little bit of tension reinforcement, for a structure that's optimized and I'm putting concrete in compression, I can actually design structures that can take significant amount of load. Just to show you the sequence of damage, here is the tensile cracking at different points in the load response. And the final failure is because of compression damage in the strut. This is the final bridge that was installed. It is offsite printed, 2 segments with a closure pore. This bridge has been designed as per standards as a pedestrian bridge, but of course our load analysis reveals that we could actually carry significant traffic loading if we had to do it. The few places that we kind of cheated was, I don't know the fatigue response, and that becomes very, very critical, particularly for bridges. So we did what the code allows us to do, and that is to use a lower allowable stress in our design if you had to do the design. And remember, the compressive strength I'm using is already a low value, the lowest compressive strength of all three directions, while I'm loading the material in the strongest direction. So there is already an inherent factor of safety built in there. On top of that, we took further reductions. So a quick review of lessons we learned from here. Basically, we can look at structural forms and 3D geometry for structural efficiency, and I can use printing to deliver those forms. And the form can be optimized within a compression form. So use concrete where it is strong and develop a form within there. And I don't need a full rectangle to give you the full capacity. I can do with less, and that is the whole point of this. And we are doing what is called form optimization and not topology optimization, because if I had turned it into a topology optimization exercise, that would be a glorious mathematical exercise, but I would end up with member sizes that are not uniform. So I may get all different sized members, but when I'm extruding, my extruded filament is always of a constant width. So this is one of the lessons that we got from here. Lessons specific to the project. The mechanistic understanding of the system response is still not there with us. I still am not with the prediction that I'm making about the capacity. While I boldly go around saying that the capacity is this, I really don't have much besides a simulated response. The continuity between the elements, and I'll stress on that a little bit, because if you look at the printed form and the physical form, I have, if you look at the top chord and the diagonal member, they're basically two separate members, but when I model it in the digital representation, it is shown as a continuous joint, and that's the way it is even modeled in our finite elements. So we need accurate representation of the force transfer that's happening at joints that are created between filaments. So this knowledge has to evolve. We need to do more testing, develop that data, and have more accurate analysis for stress transfer at such multi-filament joints. And fatigue performance of these members is still a big question mark. Now, I'll quickly use 2 minutes to go over something else that we did. That is to demonstrate this form optimization further. And we've actually developed printed on-site structures which are form optimized for a very high level of ballistic and blast protection, where you use the geometry to your advantage. This on-site printing was done in Leh at an altitude of about 3,400 meters. And this is a protective structure that was printed on-site. The surface features you see are engineered to give high level of ballistic protection. The shape itself has been optimized for a very high level of blast protection. And this is the bunker that was on-site printed. And we're taking this further for geometry-based optimization for developing these subterranean protective structures, where we come up with this geometry which is eggshell shaped. Basically, the entire structure goes into compression. I can deliver this geometry by printing and use minimal amount of material and give you very high level of resistance in blast, or for even overloads or just surcharge coming from traffic. So these are the kind of structures that we're looking at, where I can use 3D concrete printing to deliver shapes which are not possible by regular construction or casting, where I'm using the material to its advantage in a form optimized manner. So with that, I'd like to thank you for your attention. I know Venkatesh is getting a little anxious, so we'll be happy to take it.
Thank you, Professor, for your excellent presentation, and this is a very timely research. Couple of practical questions from my some problem that I faced on 3D printed recycled plastic composite with the fiber along with that. Okay, if you see the physical form with the cord and the web for the truss, there is a bonding problem between the web and the cord. So you testing with a small amount of load, which might not create a shear over there, but when you did the final element and when you go beyond the particular elastic limit, then this shear failure could be there. And even for earthquake or any type of lateral loading, this area actually really problematic. And for my industry project, I really struggling to fix up that and still keep continuing on that about this bonding between the different segment because during the printing it takes time. We are not simultaneously printing all the code at the same time, and then some part is curing and then coming back, and bonding issue always there. So how we might solve this issue actually? Thank you.
No, that's a very legitimate concern, and what we did was, if you look at the circle at the very top, so you see the top filament, and then you see the lattice, the diagonal lattice members, right? Now, during printing, depending on the precision you get, the contact between the members, that varies. So, you really have to get your printing done properly, where the precision at that particular joint becomes very important. What we have done is we do have a steel reinforcement that crosses over these two elements. So, if you look at my reinforcement template, that basically runs across the two diagonal members and goes into the top chord. So that gives me, it's almost like putting a shear stud across these two. So that's helping. What we've done is actually we have printed only these elements and tested them in different stress combinations. And we find that actually that joint with that little bit of steel reinforcement going across is able to transfer the stress, and that doesn't fail. That we have seen. And I really don't need that to have a very high capacity. All it has to do is have enough capacity in bearing, which is a given, and shear. And that little bit of steel reinforcement that we have in the form of stud helps with this particular problem.
Sure. Let's go next. Keep your question to less than 20 seconds, quickly, so that we will have more questions.
Thank you, Professor, for your excellent talk. My question is regarding the simulation work you have done on this bridge. You have loaded the structure, and then you are having a bilinear response of the stress strain, and then there is a drop.
Yeah.
So in the simulation, once the peak load is reached, then what happens is it will deform dynamically, and there is a sudden, like a lot of dynamic deformation will happen.
Right.
And we expect that the structure will fail at that point of time.
Yeah.
If it is not a displacement control and all, in real life, post-peak, there is no load carrying capacity.
Yeah.
So in the actual model, when you when you put the steel and all, that steel will not be helping out, because once that peak load is reached, after the time the structure crashes out, and then there is how the steel will help in the load carrying capacity.
Sure. Let me answer that by going back to how we got to that point, right? So what happens here is you get tensile damage. The tension ties, if you call them, the diagonal members that are in tension, those are the ones that crack first. And that little bit of steel that we placed basically is able to give some residual tensile carrying capacity. What does that do? It basically redistributes the forces within the truss then. So that allows us to carry the load from the first cracking up to a point where a full mechanism develops. So you have essentially, by the time you reach the maximum load, essentially a mechanism is developed. You have all these cracks that have formed, which are like small hinges along the diagonal members, and it's essentially a mechanism. And after that, then the final failure happens when the compressive strut fails. And that's where it becomes really dynamic. So if I don't put that steel, I won't even get to that point where the full mechanism develops. And to develop the mechanism, I need at least some residual resistance coming from the diagonal member. Now, we can still optimize it, put more steel, less steel, we have to look at it. And even the dynamic drop that you see with compressive failure can perhaps be avoided. It's something that we need to work on to get a more, I would say, ductile response from the structure.
Sure. Next question, anyone? Yeah, please.
Sir, have you checked any fire resistance of
I was expecting that question from Venkatesh, but no, not at this point. But yes, at this point, yeah, fire is not a priority.
Sure.
I hate to say that, Venkatesh, but
no, no problem. Anybody else? Yeah, please.
Good afternoon, sir. Sir, actually in 3D printing, we are going with a layer by layer concrete. So is there an interface parameter come in picture for the actual performance, sir?
Yeah. No, that's actually, I presented on this yesterday actually, as to how you homogenize the material property. and you simply cannot take it as concrete compressive with a compressive strength in the weakest direction. That's not correct. You actually have to homogenize it, and you need the layer interface properties for that. Layer interface property in compression, in tension, and tension in shear. Then you can basically develop micro-based models and use your scaling methods to go from the micro to meso to the macro. You can do that kind of an analysis, right?
Okay, one more question there.
Good morning, sir. Sir, actually, I understand that we need to print it rotated. So, did we think about the transportation stresses, handling stresses?
Yeah. This particular case, we actually off-site printed it, right? Because this is among the first cases we were trying out, and there were too many things going on. So first we said, let's develop the concept. We will print it off-site. So it is actually printed off-site. It's like a precast element. And we were very careful about lifting, and we did basically had multiple lifting points, but we did do the analysis, stress analysis with 2 lifting points. So in one of the photographs I'd shown you that we actually lifted it using straps, and we did analysis of the bridge under its own weight, suspended at those 2 lifting points. Yeah, so at this point I'm not trying to optimize at that stage. I'm just simply making sure that the bridge survives. Okay?
Okay, I have one last question, quickly.
Again, another interesting question. We are currently working on it, but this is 2 things there. I need to engineer the structure for higher levels of essentially strength and ductility. So the last example that I showed, we are actually trying to print with, I wouldn't call it ultra high performance concrete, but high performance concrete, which is very ductile. And then what you have is enhanced material ductility that results in a structure with enhanced ductility. So that's basically, I can give you a structural form that is by itself very efficient, made of a very ductile material. So the entire structural form then gives you a very high level of ductility.
Okay, last my question is, I jogged on the bridge you built in IIT Hyderabad, 3D printed bridge. Okay. I was worried whether it can stand my dynamic load, but I survived.
Okay, good, thank you.
More than one time. So you should also go and see the bridge at the IIT campus if you are visiting IIT Hyderabad. My question is, when you are building that or any other practical structures, have you given thought to how much it would have been costed without 3D printing versus this cost consideration?
That's actually a very good question, because the material that we use for printing here is almost 2 times more expensive than the regular concrete. It's a cement-rich binder. So it is more expensive. So my savings are not going to be if I don't show you saving in the structural form. So for that, then I have to design an equivalent concrete bridge of 7.5 meters span and show you that I am able to save material. And I have to save enough material to overcome the cost differential. We have done that exercise, and we find that net we save about 40% cost, including the enhanced cost of the material. So the bridge is actually only 22%, the area of the rectangle is the bridge, as opposed to a solid rectangle. So there's substantial savings in the material that overcomes the increased cost of the material itself.
Thank you very much, KVL, for excellent presentation.
Well, thank you, my pleasure. Thank you.
Okay, moving forward, we have the second plenary talk, and this will be given by Professor Narayanan 値ľľľ, again, who doesn't need any introduction. So, Professor Narayanan 値ľľľ is the Fulton Professor at Arizona State University, specializing in sustainable construction materials and innovative manufacturing methods like 3D printing of concrete. He leads key research centers funded by National Science Foundation and others. He has published extensively and is recognized for advancing green materials in infrastructure. More importantly, he spends more time in India than in the US. So I kindly invite Professor
𝗗𝗴𝗃𝗶𝗵𝗿 to give his plenary address.
Thank you, Venkatesh. I had to come soon enough to stop Venkatesh from telling more. Yeah, you want the... Yes. Do you have the collar mic? Collar. Oh, it's okay, it's okay. No, it's not showing up. It's not projecting. No, it's not projecting yet. No, it's not projecting. It's not. All right. So just enough good morning. In 2 minutes, I would have lost the good morning. Thank you for the invitation. Wonderfully well organized, and I should congratulate all the organizers for doing such a phenomenal job in taking care of all of us. So thank you for that first. We had two beautiful bridge talks, so I'll slightly change topics and go into more of the smaller scale stuff that makes up bridges and talk about the idea that we have been constructing, we have been doing things in a certain fashion for all this time. Is there a way to change? Is there a need to change? I think that's fairly straightforward argument that there is a need to change. I will look at, is there a way to change and way to change more sustainably, more economically, and effectively in a way that helps development happen in a better fashion. So that's what I'm going to be talking about. Just acknowledge all the people that we have worked on several of these topics over. So this is a compilation of work that has happened over the last 5, 6, 7 years with different funding agencies and different people and different senders that have funded our work. So gloom and doom scenario. This is what you would have heard. Climate change, concrete, big problem, right? And the most destructive material on earth, there's even, and that's best of 2019. So, you know, we don't have to, for all of you, this should not be music to anybody's ears. Best of 2019 saying concrete is the most destructive material. We have to abandon concrete to fight climate change. But if you abandon concrete, what do we do with the kind of infrastructure development that we need across the world? India, China, Africa, all these countries need tremendous amount of infrastructure. What other material will you use? What other material will you use at this cost and this versatility that you can get? So the question of, it's a very nice newspaper article, can spur a lot of thought. So can you do something else? But from somebody who is using concrete all the time, we should also think about, is there any merit in that argument? Is there at least some amount of merit in that argument that there is some destruction happening with concrete? There's this like statistics, right? You can show it in whichever way you want and convenience yourself in whichever way you want. So I've heard people say that cement carbon impact is about 8% total global carbon impact to 4% to 16%, depending on who you talk to and what time of the day and what they had for dinner. So it's a very, very flexible argument. But if you look at facts, and if you look at embodied carbon dioxide versus embodied energy, concrete is actually one of the lowest carbon and lowest energy materials. The problem is the scale at which we use concrete. The problem is the quantum at which we use concrete. And therefore, if you have so much of infrastructure and buildings to build, you pretty much are out of luck. I mean, if you look at cement, that's a little more, but if you go to all these end of these materials, plastics and aluminum and bitumen, they have much higher carbon or energy impacts, but then the volume of use is less. So again, there is a need in that sense to make concrete more carbon efficient if we still want to use the same amount or more amounts of concrete. So cement production, again, I'm not going to go through it. I'm preaching to the choir. You have to extract raw materials. They have to go through a whole sequence of grinding, crushing, pyroprocessing, packaging, transporting, and it adds up with respect to carbon impact. But if you look at where the most impact comes from, that's in this manufacturing step, where you take limestone, you heat limestone to 900 degrees Celsius to make it calcium oxide, and then you fuse the calcium oxide with silica and alumina to form what you get as clinker, and then you grind the clinker to get cement. That process of calcination, where you heat
the raw materials and then fuse with silica and alumina, that's where the highest amount of carbon impact and energy impacts are. Now, the first question is chemistry is arresting us right there. Calcium carbonate, to become calcium oxide, you have to take carbon dioxide out. There is no other way, right? You are stuck with chemistry there. Now, okay, then you say, I don't want calcium carbonate. I can use calcium silicate. You end up with another problem. We don't have as much calcium silicates as calcium carbonates, and calcium silicate transformation to calcium oxide to take the stable silica out is an even bigger problem. You have to do other methods, not just heating. So now you end up with difficulty in processes, you end up with having to have that extra CO2. So, and then again, that's a process that we talked about. But if you look at the emission impacts of concrete as a whole, so cement, of course you do limestone and heat, you get clinker, plus you add SCMs, raw material, cement plus aggregate plus water. Somebody smartly put in air also, just to make sure that your voids are, you're not complaining about the voids. And then you mix and you get concrete. But at the end of the day, 88% is attributed to cement, 80 to 85% depending on who you talk to. So cement still is the biggest contributor to emissions and energy impact of concrete. And if you look at global carbon impact, cement production generates the most emissions per revenue dollar. Again, this is beautiful math where you increase the denominator and you get a small value, or reduce the denominator and get a lower value. Again, people use this nicely, and if you're a consultant having to show that, and you're arguing for somebody who doesn't want to show concrete in good light, you can use a very small denominator. But again, generally, you see that per revenue dollar, kilograms of CO2, cement has the highest value. Even iron and steel, which has to go to a much higher temperature, has a much lower value, but steel is much, much more expensive than cement. Cement is the cheapest material. Again, I used to tell my students when I teach that you go to Lowe's, Home Depot, the big stores that sell cement and steel for home repair stuff, you can actually get a bag of cement sometimes cheaper than a bag of pottery soil that you use to plant soils, right? So it's so cheap. And that's because of the scale in which we produce cement. Emissions, if you look at different countries in the world, you can see China, of course, blood red, because they are producing a lot of cement and doing a lot of emissions, therefore that number is coming down. India is not too far behind, US is not too far behind. So, and then you can see gradation of colors. There's pretty much nothing here, but this will keep picking up. Canada, of course, not much of construction there. It's a huge country. Australia, similar story. So, life cycle emissions. Cement manufacturing and aggregate production accounts to close to 80% of life cycle emissions of cement and concrete. That's a fact that we have to live with. So the question is, how do we mitigate it, right? And this is from US Department of Energy. This is typically a United States scenario. Typically in India, it's slightly different. But if you look at it, at the end here, buildings constitute about 50% of consumption of cement, and all the other infrastructure constitutes the remaining 50%. India, probably buildings are 70, 75%, infrastructure is 20, 25%, right? In the US, most of cement production goes into infrastructure. But again, US produces only 100 million tons out of the 4.5 billion tons of cement that's produced. We are only 4% of the global cement production or cement consumption. And most of it goes to infrastructure, whereas India, the scale is going up. India is probably at about 150 million now, or 250 million now, projected to go further up. So the scales will tilt in developing economies pretty fast. And especially, like your director was talking in the morning, 2047, Viksit Bharat, you need a lot of construction, a lot of infrastructure by 2047 to happen. And this scale is going to tilt phenomenally, so that the emissions will have to be curtailed. Right, so how do we mitigate? Phenomenally, first question that is asked and the first answer that you get from anybody who does cement, use lots of waste materials. Use SCMs, use less clinker, use all of these. Which is okay in a place like India where you have plenty of fly ash, plenty of SCMs. In the US, we are pretty much out of fly ash. Really no fly ash is available or very little fly ash available because coal power plants have been shut down. Maybe coal is coming back in the US in the name of clean coal. We don't know what that is, but we are getting clean coal back. So maybe it'll turn, but right now we don't have coal, so we don't have fly ash. The other issue then we can do is to find out alternate process heat. Don't use petroleum, don't use fossil fuels that create CO2, use something else to heat, use solar to heat. Think about getting solar to 1200, 1400 degrees Celsius. You can't even get your water heater, boil your water with solar effectively. Try getting it to 1200, 1400. Solar is a problem. There are methodologies to overcome that, but again, they're going to be very expensive solutions. So what are the other pathways and what are the economical pathways that we can look at? I'll skip this slide. So if you talk about clinker supplements, which is vastly talked all over the world, or most parts of the world, here is some very interesting statistics they've come up with. Alternate binders, new innovative SCMs, 2020 to 2030 time scale, they're going to go up, but they're going to come down 2030, 40, 40, 50, they're going to come down. Green clinker pilot plants are rolling out in several parts of the US. Again, this is mostly US scenario. And at scale clinker from carbon capture, storage, that's going to go up. That's a projection. Again, carbon capture might not be as lucrative as it was last week, literally last week, for reasons that if you follow US news, you will know. So that's not going to be the solution effectively, I think. So what else can it be? Natural SCMs and fillers, lots of natural SCMs are becoming common. You can do aluminosilicates out of dig out of the earth. We'll talk a little bit about that. There is gray clinker talk where you phase out some of the old plants and come out with pure gray clinker assets being closed out, which is happening in the US a little bit. There is very little pure OPC plants now. Everybody is moving into Portland limestone cements, PLCs, right? Which is the precursor to limestone calcined clay cements, which is LC3, which is the natural SCMs. So lots of different movements in that scenario. But if you look at supply and demand side strategies, these are your conventional supply side strategies. You reduce your clinker to cement ratio. You reduce your clinker content. I don't know, Indian cements are probably at about 0.85, I think. US cements are about 0.82. There are some European cements that have a clinker to cement ratio of 0.7, but the global average still hovers around 0.8-ish, clinker to cement ratio. Electricity decarbonization, that's a total new policy decisions. I mean, how do you go away from fossil fuels and come up with other ways of creating electricity? India is doing better with lots of hydroelectric projects, with lots of nuclear projects coming in. In the US, we pretty much had no nuclear plants done in a long time. The closest we came to building one was in 2011, and as clockwork, Fukushima struck and we stopped everything. So there's really no alternate energy sources that are coming up other than the renewables, which is solar and wind and geothermal for that matter. Supply side strategies, low carbon cement chemistries. If you keep a lookout, you will see lots of different low carbon cement chemistries. You have calcium silicate cements, calcium aluminate cements, you have magnesium based cements. A lot of these low carbon cement chemistries are there. Carbon capture and utilization, I wouldn't go too much into it. And then there's a bunch of material sides, demand side strategies, which you heard, optimization, for example, like you saw in 3D printing just before, really a demand side strategy where you do material efficient design. You heard in the first talk on bridge design, where you can actually make it much more efficient through design strategies. Those are all demand side strategies. If you look at materials efficiency, where is the world going to? At least when I say world, in the US, we have the habit of saying world is the US, right? Because we don't see any news other than what is happening in the US. So Portland limestone cement is what is picking up, and it's happening in most parts of the world in some fashion. Blended cements with fly ash in India, this is a great option. It still will be a great option. Blended cement with steel slag, I won't even talk about it in the US because we don't have steel slags available. All steel slags are accounted for. We don't really have new steel plants. And even if there are steel plants, there are electric arc furnace slabs, no more blast furnaces, right? So you get into trying to solve one problem, and therefore you end up with not enough materials for concrete the way we want to use it. And then limestone, calcined clay cements at the bottom. Where is my D? Okay. So limestone, calcined clay cements here, which is quite efficient in carbon reduction. So now the question is, how do we extend this further and how do we apply it? So let's talk about a few of those things. Portland limestone cements, the science has been proven for quite a long time. 10-15% of limestone ground back into the cement so that you can save that 15% clinker. Great strategy. What happens is that a little amount of that limestone can react with the aluminates available to form mono-hemi-carbonates, in addition to the CSH gel that you form to give you additional properties. You save extra cement. There's a bunch of theory as to how this happens, but you don't have to worry too much about it. This can be done. So in the US, we have what is called a performance-based specifications for cement. So you don't have to go and do the chemical composition matching all the time. You can do performance-based. So ASTM C595 and C1157 are the two performance-based standards that you can do based on performance. What do you want? 40 megapascal strength at this time? Get it, move on, make sure that nothing else happens. Right? So that is, and therefore these cements are now much more common. So here are two cement plants, just an example. This is Cal Portland cement plant in California and Ash Grove's plant somewhere in Missouri, I think. These two plants have completely converted, two examples of plants that have completely converted into Portland limestone. They cannot make normal OPC anymore, even if they want, without changing their processes, right? So about 10 to 15% of emission reductions, that translates into, if you're making 1 million tons of cement, it's about 100,000 tons of CO2 every year reduction. There are lots of concrete paving projects in the US. Concrete pavements are the biggest consumers of concrete, and then bridges. Buildings are a very small fraction generally. So there are lots of paving projects that are happening, and I'm showing the one in Utah because Utah is cold, and they have done this with resistance against freezing and thawing, resistance against salt scaling, all of those durability criteria that you may have normally problems with. And then if you look at Portland Cement Association, which is now called the American Cement Association, because we are all about Make in America and Make America Great Again. We have now the American Cement Association. They are now using a lot of educational items about improving Portland limestone cements and see how that can be implemented. Like I said, limestone is very good if you can make it react with some reactive aluminates. Cement has some aluminate, right? C3A. If you have ever looked at a mill certificate of cement, you will see something called tricalcium aluminate. So cement has some aluminate, which the carbonate can react with to form simple. You can let little kids know. Carbonate and aluminates, carboaluminates. No much fancy naming there. You can form carboaluminates, and the carboaluminates can increase your strength a little bit. You can increase your solid formation, solid products, increase your strength. So that's the whole idea, and what I'm showing here is some thermodynamic simulations. Metakaolin is a very reactive aluminate, and you can see here mono and hemicarbonate formation, plenty of monocarbonates and hemicarbonates. And when you add metakaolin plus 30% limestone, this is your typical LC3, right? 15% metakaolin, 30% limestone, 5% gypsum. That's your LC3 cement if you know limestone calcined clay cement. And you will see lots of monocarbonate formation. Hemicarbonates are converted to monocarbonates as well. So you get system stability that way. And if you look at it here, you have pretty much reduced 50% of your clinker. Right? So that is massive reduction in terms of cement. Again, this also talks about availability. Like I said, in the US, fly ash is not available much. This is the scenario of what we have. Silica fume, very little. Natural pozzolans, not much. Slag and fly ash, also very little. Plenty of Portland cement. But look at limestone, look at calcined clays, or I should say clays. Plenty of clays available. Now that could be slightly different in Indian scenario because you don't want to take clays out of agricultural land and then spoil agriculture in the name of making cement. That's a bad strategy, right? But if you have low grade clays, if you have Waste materials that are aluminosilicates, definitely that can use it. In the US, lots of farmers get money not to cultivate, just leave their plot empty, so the government gives them money so that you don't have to ask for further subsidies. So there is plenty of land available and there's plenty of clay available to mine, which companies are efficiently utilizing now, right? So this is your typical Portland cement, and this is your calcined clay. So when you get to here, you have no CO2 from gypsum, no CO2 from limestone, a little bit of CO2 from calcining the clay, but you save a lot of clinker, so you save all of these, and then there's lots of CO2 saved as compared to OPC. So that's the idea, that's a strategy. So ternary blends with LC3 systems, one of the biggest problems with such cements is very low early age strength. So 1 day, 3 days, you get very low strengths if you don't play around with it. So the strategy that we are looking at and some of the new stuff that we are looking at is how do we do it? Can we co-calcine limestone and clay? And companies are trying to do that. Can you put some limestone and clay together? What happens is you calcine the clay completely. That's about 600 degrees Celsius. Your limestone needs to get to 900. So at 600, limestone is only a little bit calcined. When you get a little bit calcination around the carbonate grains, you get a little bit of calcium oxide. And then you kickstart the reactions with that calcium oxide, you get very early strength. I'll show you the reactivity curves. You can see here. That's your normal OPC, heat of hydration, reaction early on. You see what's happening. That red one, by the way, is LC3. So LC3 still does that because of the calcined clay. But if you add a little more calcium oxide through that additional carbonation, you get this very quick peaks early on. And you have this aluminate and silicate peaks picking up much, much further. That gives you added strength. So what that does is you can now start to replace more cement, right? You're getting that extra strength. You can replace more cement. So you can do up to about 70%, 75% of cement, of clinker can be replaced. Again, if clinker reduction is your strategy, you need that. Now, what does that do with admixtures? Wonderful story. If you're an admixture manufacturer, you will be very, very happy because it will need a lot of admixtures to do that. The other story is how do you activate clays? Clays are not normally very reactive because they have these tetrahedral sheets of silica and octahedral sheets of alumina that are very happy with each other. They don't want to do anything. So how do we make them react faster? You can really, really grind them, mechanically grind them, break them into much, much more finer at crystal structure levels and create much more reactivity. So this is non-activated. I'll quickly show you what happens here. You need about 600 degrees Celsius to burn them, but if I mechanically crush, I need only about 200 degrees Celsius to burn that water off, which means I need much, much lower energy now. This is for kaolin, that's for montmorillonite. You can get up to 50 degrees Celsius. You can just burn it off very quickly, make something very reactive by just grinding. So again, simple processing techniques, not simple in the sense that manufacturer can do it fairly easily, processing techniques to make things better. Again, I'll skip the NMR structure because alumina from 6 coordination, which doesn't do anything, goes to 4 coordination, which is very reactive, 4 oxygen with alumina rather than 6 oxygen with alumina. But what are the other options? You can carbonate cements. You can make cements carbonate and then absorb some CO2 that way. You can use fly ash to carbonate stuff very, very well. Those who are working with alkali activated cements, with alkalides they'll carbonate even more. Don't ask me if carbonation is a problem here. That's a totally different story. For this, carbonation is different from the carbonation for concrete that causes steel corrosion. That's a different story. But you can create carbonated products. You can mineralize it. But I've talked quickly. Venkatesh, how much time do I have? 5 minutes?
You have about 5 minutes.
Very nice. That's what I planned. So quickly talked about some low carbon alternate manufacturing methods. So if all of these clinker reduction strategies are great, but can cement companies think about reimagining manufacturing of cement? And that's some of those things that we are working on now. Can we completely reimagine cement manufacturing? Can we think about ways in which we can make cement differently with almost no CO2? Sound science fiction? Kind of, right? But I'll show you a few options to do it. It still is fiction. It still is science for sure. Fiction, I'm not so sure. We'll see that. So you can do electrical calcining. 1200 degrees, electricity can help you calcine. If that electricity is provided by a renewable source, that calcination becomes carbon-free. Now, I'll show you a few ways that you can tweak this whole process, and there is plasma as well. So here is current average emissions, just to set the stage, current average emissions from cement production. This is direct combustion. These are the direct process emission, which is your calcium carbonate becoming CO2, and this is electricity production, right? If you use alternate fuels, you can take away all this fuel part, you just drop it down to this part, and then amine-based oxy-fuel. But if you do an electrified calciner or kiln, you take this thing off completely. You have lots of electricity need, but this process emission is gone completely, assuming that, now that's a key here. If I calcine limestone alone, I get pure CO2, correct? Whereas in the current cement manufacturing, you are getting CO2 mixed with a lot of other gases that is very difficult to separate. And then if I do an electrochemical process, I have no process emissions. I'm not even breaking calcium carbonate into CO2 at all. And I'll show you quickly one slide on that. So here is one way of doing it. You have an electrically heated calciner, which basically means limestone is calcined by itself, not as a raw meal with everything, just limestone heated, which means you get pure CO2 that you can take off and sequester and do something else. And then you have rotary kiln. Here you start mixing the remaining things and you create it. Your pure CO2 can be captured. Right? You can integrate it with the CCUS method. You can co-locate it with a facility that needs CO2 as a raw material, like chemicals. Ethylene, acetylene, all of them need CO2. You can co-locate it, right? The CO2 gets used, your cement comes out almost CO2 free, if that's one option. The other option is electrochemical technologies. This is a little more into fundamental science regime, where you can start breaking calcium carbonate into calcium hydroxide, essentially, not calcium oxide, into calcium hydroxide by electrochemistry, right? And this can be done in 2 or 3 different ways. You can do a high temperature electrolysis using molten salts. You can do room temperature electrolysis. You can do recycling in seawater, where you can do ion exchange. There are multiple ways of doing it. But all electrolysis method essentially creates only calcium hydroxide. With that, you have to fuse silica and alumina. You need something else. And that something else typically is either a plasma or some other renewable technology, which I'm not talking about now just for lack of time. So the idea is, if you're looking at all cement reduction technologies, yes, clinker reduction is great. You should still do clinker reduction. You should stress the clinker reduction as much as possible. But if our infrastructure growth goes like that, there will come a time where clinker reduction also will fall short. And what do we do at that time? Some of these new technologies are the precursors that we should look at in terms of understanding how we can completely reimagine manufacturing of cement. The advantage, now this chemistry and this process allows you to manufacture many things together. And cement doesn't have to be this 500-acre plant with another 10,000 acres of limestone mine. You can actually make it much more portable, because you don't really need this 50-meter, 100-meter long kiln. You can actually shorten this process completely. Capital expenses, don't talk to me, don't ask me at all, because I don't know, right? There'll be extreme capital expenses involved, but at some point of time, if environment trumps economics of this, there might be a time that you can use it. In the US, we are actually starting some of these pilot plant works, electrochemical pilot plants. A company called Sublime Systems, if you can look at it, they are actually doing this. They are creating, I think, 100,000 tons of cement, or they plan to create 100,000 tons of electrochemical cement. So these are coming. These are technologies that are coming. Just to give you a preview of where materials is going towards sustainable structures. And all of this, again, I want to emphasize the fact that all the materials that I talked about have exactly the same properties of conventional, ordinary Portland cement or current materials that you know, so that your standards and specifications doesn't have to be changed. Because changing standards and specifications is a huge job. It'll pull us back further. So the idea is to create the same material with a different manufacturing process. And therefore, the focus now is on manufacturing, because we know what the chemistry is, what kind of manufacturing systems will work, and what kind of technologies would be needed. Thank you very much. I think I'm on time.
Thank you very much, Narayanan. Excellent presentation again. Can you hear me? Yeah, okay, good. So now we are going to take few questions. So who wants to go first? Keep the questions short so that, we will take more questions, Yeah.
I knew that because this is...
That's a perfect presentation.
Exactly. No, I'm standing between all of you and lunch.
Yes. No. Which he doesn't like standing. He wants to sit.
I want to sit.
Go to the next level.
No, I don't want to say that here. Come on, Venkatesh.
Sure. So, some of the statistics you presented, all this carbon reduction, have you taken, new structures are much different based on the previous structures. We optimize the structural design component, not necessarily for carbon reduction, but we are doing much of this for cost cutting, how to save some money. So if you include all that, still cement, still concrete structures have same amount of carbon footprint?
That is based on the amount, that's based on the concrete used, right? So it's based on a unit volume of concrete. So if you reduce the overall volume of concrete, the structure itself becomes more efficient, but the concrete by itself is not more efficient, right? So it is based on a unit volume. So all calculations, all the numbers are based on a unit volume of concrete. And so what you need is to reduce the carbon impact of that unit volume of concrete, which can be attained through these material strategies. So that's the idea.
I see. Yeah, please. Yeah.
Sir, you have mentioned alternate methods of getting the carbon out. So, can you think of a process wherein you can make the same thing and then use that CO2 carbon to make a carbon fiber and then make both work together?
Good question. So, some of these sequestered carbon, Oak Ridge National Labs, for example, in the US, is actually doing a big project to use sequestered carbon to create carbon materials, including carbon fibers, graphene, and several of those carbon nanotubes, all of that. So there are projects that they're doing it. But then what happens is with a conventional, for example, graphene, which is really expensive, if you use a certain flash joule heating process or a detonation synthesis process, a pound of graphene, which is less than half a kilogram of graphene, costs you about $500, right? But by using the CO2, and these processes emit CO2. But if you want to capture these CO2 and make these materials, you are talking about four times higher cost, right? So the cost is now a detriment, but again, it's a processing thing, and as time goes in, processes will become efficient, but that is a definite possibility, and that's why I showed chemicals. Converting a captured CO2, especially a hot CO2 from a kiln or a furnace, to a chemical like acetylene or ethylene is a much more easier process than creating carbon fibers. Yes, there's a question.
Yeah, please.
Sir, if we can increase the blend numbers of OPC, means indirectly we are going to increase the reactivity of that. And means that can be a point where we can utilize that binder for more volume of concrete making. Whether there has been the possibility so that we can, if we are talking about really to save the carbon credits.
So if you increase the reactivity of cement, if you increase the reactivity or blend fineness from 350 meters square per gram to 500 meters square per gram, which I think many of the cement companies are already getting there in India. If you will reduce the cement content by 200 kilograms per meter cube, you have a valid point. But are we reducing the cement content when we increase the blend's fineness? Because we increase the blend's fineness to further increase the strength. That's the idea, right? So our blend's fineness increase to further increase the strength. Of course, forget about all the heat of hydration issues and shrinkage cracking that comes along with it. But the fundamental idea is to increase the strength. So if you can increase the strength and reduce the cement content by 200 kilogram per meter cube, I have no problem. We should do that. And if that's the easiest way, that should be perfectly fine. But you're still using pure OPC clinker to do that. While the problem is that even if you have a very fine cement, by the time you make a high performance concrete, only a fraction of a cement is hydrating. The rest of it is staying there as a very expensive carbon intensive filler. The question is, why not change that? Why not reduce the clinker content, reduce the amount of cement, make the available amount of cement work much harder, use other fillers to do what a hard unreacted cement will do. That's the whole idea of optimizing the cement production process.
Okay. Thank you. Thank you, Narayanan.
Thank you, thank you.
So, thank you all for an excellent session. Now I am going to give it to...
Thank you, Professor 𝗘𝗃𝗏. I now request our plenary chair, Professor Kodor, to kindly present token of appreciation to our plenary speakers. Sir, I kindly request you to come on the dais. First, we have Professor Mike Schlaich. Professor Subramanyam, may we have you on the dais? Professor 𝗘𝗃𝗏, please come on the dais. One minute. Now I kindly request Professor Schlaich to present the token of appreciation to our plenary chair, Professor Kodor. We request all the dignitaries to kindly proceed to the ground floor for the group photograph. All participants are requested to download the app for the lunch. If you have any queries regarding that, you can consult the help desk. Lunch will be served on the ground floor from 12:40 to 2 p.m. After lunch, we will begin the technical sessions in the respective classrooms. Thank you.